1.1 Data Science Process and Components. Learn history of statistics, science of statistics, application of statistics data analytics and their connections with data science. 1.2 Data collection and preparation. Types of studies. Dependent variable vs independent variable. Populations and parameters. Samples and statistics. Data collection. Types of bias. 1.3 Descriptive statistics. Descriptive statistics versus inferential statistics. Break. Parametric vs non-parametric test. Introduction to EDA. Lecture 1. History of data science. In 2001, William S. Cleveland introduced data science as an independent discipline, extending the field of statistics to incorporate advances in computing with data in his article Data Science, an action plan for expanding the technical areas of the field of statistics, which was published in Volume 69, Number 1, of the April 2001 edition of the International Statistical Review/Revue Internationale de Statistique. In April 2002, the International Council for Science, Committee on Data for Science and Technology, CODATA, started the Data Science Journal. A publication focused on issues such as the description of data systems, their publication on the Internet, applications, and legal issues. In the 2012 Harvard Business Review article Data Scientist, the sexiest job of the 21st century, and asserts that a data scientist is a new breed, and that a shortage of data scientists is becoming a serious constraint in some sectors. Statistics is the science of learning from data and is a crucial component of data science. Statistics research focuses on data collection and modeling, and there is little work on developing good questions, thinking about the shape of data, communicating results, or building data products. Data science is also known as data-driven science, is an interdisciplinary field about scientific process and system to extract knowledge or insights from data in various forms, either structured or unstructured, which is a continuation of some of the data analysis fields, such as statistics, machine learning, predictive analytics, etc. Why study statistics? To evaluate printed numerical facts. To interpret the results of sampling or to perform statistical analysis in your work. To make inferences about the population using information collected from the sample. To test some hypotheses about the population based on sample dataset. What do statisticians do? Gather data. Summarize data. Analyze data. Draw conclusions and report the results of their analysis. Observational. A study where a researcher records or observes the observations or measurements without manipulating any variables. These studies show that there may be a relationship but not necessarily a cause and effect relationship. Experimental. A study that involves some random assignment of a treatment, researchers can draw cause and effect, or causal, conclusions. An experimental study may also be called a scientific study or an experiment. Example, we want to decide whether Advil or Tylenol is more effective in reducing fever. Method 1. Ask the subjects which one they use and ask them to rate the effectiveness. Is this an observational study or experimental study? This is an observational study since we just observe the data and have no control on which subject to use what type of treatment. Observational. A study where a researcher records or observes the observations or measurements without manipulating any variables. These studies show that there may be a relationship but not necessarily a cause and effect relationship. Experimental. A study that involves some random assignment of a treatment, researchers can draw cause and effect, or causal, conclusions. An experimental study may also be called a scientific study or an experiment. Example, we want to decide whether Advil or Tylenol is more effective in reducing fever. Method 1. Ask the subjects which one they use and ask them to rate the effectiveness. Is this an observational study or experimental study? This is an observational study since we just observe the data and have no control on which subject to use what type of treatment. Method 2. Randomly assign half of the subjects to take Tylenol and the other half to take Advil. Ask the subjects to rate the effectiveness. Is this an observational study or experimental study? This is an experimental study since we can decide which subject to use what type of treatment. Thus, the self-selection bias will be eliminated. Causation. It is very important to distinguish between observational and experimental studies since one has to be very skeptical about drawing cause and effect conclusions using observational studies. The use of random assignment of treatments, i.e. what distinguishes an experimental study from an observational study, allows one to employ cause and effect conclusions. Ethics is an important aspect of experimental design to keep in mind. For example, the original relationship between smoking and lung cancer was based on an observational study and not an assignment of smoking behavior. A variable is any characteristic, number, or quantity that can be measured, counted, or observed for record. There may be many variables in a study. The variables may play different roles in the study. Variables can be classified as either explanatory or response variables. Response variable. Variable that about which the researcher is posing the question. May also be called the outcome or the dependent variable or target variable. Explanatory variable. Variable that serve to explain changes in the response. They may also be called the predictor or feature or independent variables. Note: a variable can serve as an explanatory variable in one study but response in another. It depends on business problem. For example, assume you have a data set of customers of one bank that got loans. If you want to predict loan amount is target, response/dependent variable/output/outcome/label, and other variables are independent variables, features/predictors. If you want to predict loan status, if each customer paid his/her loan, loan status is target, dependent variable/response/outcome/output/label, and other variables are independent variables, features/predictors/input variables. If you want to predict purpose of loan is target, dependent variable/response/outcome/output/label, and other variables are independent variables, features/predictors/input variables. The terms response, dependent variable, output, outcome, and label are often used interchangeably in the context of data analysis and machine learning, depending on the specific domain or context. They all refer to the variable you are trying to predict or explain. The terms independent variables, features, and predictors are often used interchangeably in the context of data analysis and machine learning. They all refer to the variables used to predict or explain the outcome or target variable. The independent variable is the factor that you purposely change or control in order to see what effect it has. The variable that responds to the change in the independent variable is called the dependent variable. It depends on the independent variable. A scientist is testing the effect of light and dark on the behavior of moths by turning a light on and off. The independent variable is the amount of light and the moth's reaction is the dependent variable. In a study to determine the effect of temperature on plant pigmentation, the independent variable, cause, is the temperature, while the amount of pigment or color is the dependent variable, the effect. Populations and parameters. Population. Any large collection of objects or individuals, such as Americans, students, or trees about which information is desired. Parameter. Any summary number, like an average or percentage, that describes the entire population. The population mean mu, the Greek letter mu, and the population proportion p are two different population parameters. For example, we might be interested in learning about the average weight of all middle-aged female Americans. The population consists of all middle-aged female Americans, and the parameter is mu. Population mean. Or we might be interested in learning about the proportion of likely American voters approving of the president's job performance. The population comprises all likely American voters, and the parameter is p, population proportion. The problem is that almost all of the time, we don't or can't know the real value of a population parameter. The best we can do is estimate the parameter. This is where samples and statistics come into play. Samples and statistics. Sample is a representative group drawn from the population. Statistic. Any summary number, like an average or percentage, that describes the sample. In other words, a descriptive measure of a sample is called a statistics. The sample mean, and the sample proportion, are two different sample statistics. For example, we might use the average weight of a random sample of 100 middle-aged female Americans, to estimate mu, the average weight of all middle-aged female Americans. Or we might use the proportion in a random sample of 1,000 likely American voters who approve of the president's job performance, to estimate p, the proportion of all likely American voters who approve of the president's job performance. Assume we want to find the average height of all grade 12 students in Canada. Population equals all grade 12 students in Canada. Parameter equals the average height of all grade 12 students in Canada. Since it is time consuming and needs a lot investment, we decide to randomly select 200 grade 12 students in Canada, and we measure height of them, then calculate average height of them, descriptive statistics. Sample equals 200 grade 12 students in Canada. Statistic equals the average height of 200 grade 12 students in Canada that we selected. Then based on statistic we try to predict parameter, inferential statistics. Because samples are manageable in size, we can determine the actual value of any statistic. We use the known value of the sample statistic to learn about the unknown value of the population parameter. Techniques of describing data in ways to capture the essence of the information in the data are called descriptive statistics. For example, the sample mean is a descriptive statistic. To draw conclusions from data about the population is called inferential statistics. Here is a picture that demonstrates inferential statistics. Descriptive statistics describe what is going on in a data set by summarizing existing data and prediction based on them to a larger population, called inferential statistics. How can we get data? How do we select observations or measurements for a study? There are two types of methods for collecting data, non-probability methods and probability methods. Non-probability methods. These might include convenience sampling, haphazard collecting data from subjects who are conveniently obtained. Example, surveying students as they pass by in the university's student union building. Gathering volunteers, collecting data from subjects who volunteer to provide data. Example, using an advertisement in a magazine or on a website inviting people to complete a form or participate in a study. Probability methods. Simple random sample, making selections from a population where each subject in the population has an equal chance of being selected. Stratified random sample, where you have first identified the population of interest, you then divide this population into strata or groups based on some characteristic, e.g. sex, geographic region, then perform simple random sample from each strata. Cluster sample, where a random cluster of subjects is taken from the population of interest. For instance, if we were to estimate the average salary for faculty members at Penn State, University Park campus, we could take a simple random sample of departments and find the salary of each faculty member within the sampled department. This would be our cluster sample. Random sampling, when every unit of a population has a known chance of being included in a sample, such a sample is called a probability sample. Let us discuss each type of sampling under this category. Simple random sampling, in this method, sample units are selected randomly. This is similar to drawing names from a hat. Example, suppose you want to find the average internet usage per person in India. You can simply write the names of all the Indians on small pieces of paper and put them in a hat. You can then draw, say, 100 names and calculate the average for these 100 Indians. This sampling method is applicable only when your population is finite, such that you can list all its units, and you understand it completely. This process is thus quite cumbersome when working with large populations. Stratified random sampling, here, people are divided into subgroups and then selected randomly. Nevertheless, this is done in such a manner that the proportions of these subgroups in the final sample equals their proportions in the population. Example, again, suppose you want to find the average internet usage per person in India. Note that 70% of Indians live in rural areas and 30% live in urban areas. So, you would put the names of all the rural Indians in, say, hat A and the names of all the urban Indians in another hat, B. Then you would draw 70 names from hat A and 30 names from hat B. Now, you would again have a sample of 100 Indians, although this time, your sample would be more representative of the population as the proportions of rural and urban Indians would be the same as those in the population. Cluster sampling, in this sampling method, a population is divided into clusters and then samples are drawn from some of these clusters using simple random sampling. Difference between cluster sampling and stratified sampling. For a stratified random sample, a population is divided into strata, or subpopulations, before sampling. However, in cluster sampling, you will only study selected clusters. For example, let us consider the problem of finding the average internet usage per person in India. It would be difficult to obtain a list of all Indians and collect data from a random sample across the country. However, a list of cities may be available, and you can collect data from a subset of these cities. Systematic sampling, in this sampling method, sample units from a larger population are selected in accordance with a random starting point but with a fixed, periodic interval. An example of this is when you select every third person on a list of a population, as shown in this image. Non-random samples, when we cannot calculate the odds of any population unit being included in a sample, then such a sample is called a non-probability or non-random sample. Let us discuss the two types of non-probability sampling. Convenience sampling. Convenience sampling, as the name suggests, is sampling based on the researcher's convenience. Example, you want to find the average internet usage per person in India. Only this time, you simply ask 100 people around you about their internet usage. Clearly, this sampling method has potential to be extremely biased. The only good part here, probably, is that it is a relatively convenient sampling method. Judgment sampling. This is a purely judgment-based sampling approach. Sample units are chosen based solely on the researcher's knowledge and judgment. Example, suppose you wish to study the different faiths in India. It is advisable to use judgmental sampling to select people of different faiths as religion is considered to be a sensitive topic. I.e., in simple random sample doesn't matter each selected member belongs to which group. In stratified and cluster sample first we divide all population to some groups based on some characteristic and then, if we randomly select some members from all groups, this called stratified random sample. If we randomly select one group and assume all members in that group, this called cluster sample. Airline company survey of passengers. Let's say that you are the owner of a large airline company and you live in Los Angeles. You want to survey your LA passengers on what they like and dislike about traveling on your airline. For each of the methods, determine if a non-probability method or a probability method is used. Then determine the type of sampling. A. Since you live in LA, you go to the airport and just interview passengers as they approach your ticket counter. B. You have your ticket counter personnel distribute a questionnaire to each passenger requesting they complete the survey and return it at end of the flight. C. You randomly select a set of passengers flying on your airline and question those that you have selected. D. You group your passengers by the class they fly, first, business, economy, and then take a random sample from each of these groups. E. You group your passengers by the class they fly, first, business, economy, and randomly select such classes from various flights and survey each passenger in that class and flight selected. Answers. Non-probability method, convenience sampling. Non-probability methods, volunteer sampling. Probability method, simple random sampling. Probability method, stratified sampling. Probability method, cluster sampling. There are advantages and disadvantages to both types of methods. Non-probability methods are often easier and cheaper to facilitate. When non-probability methods are used, it is often the case that the sample is not representative of the population. If it is not representative, you can make generalizations only about the sample, not the population. The primary benefit of using probability sampling methods is the ability to make inference. We can assume that by using random sampling we attain a representative sample of the population. The results can be extended or generalized to the population from which the sample came. A lot of thought has been put into the science of the design of survey questions. Key design principles. Keep the questionnaire as short as possible. As short, simple, and clearly worded questions. Start with demographic questions to help respondents get started comfortably. Use dichotomous, yes-no, and multiple choice questions. Use open-ended questions cautiously. Avoid using leading question. Pre-test a questionnaire on a small number of people. Think about the way you intend to use the collected data when preparing the questionnaire. In statistics, bias can affect the collection, analysis, interpretation, and publication of data. Here are some common types of bias in statistics. Selection bias occurs when the sample is not representative of the population being studied. For instance, you are interested in the attitude of female students regarding campus safety, but when sampling you also include males. In this case, your population of interest was female students, however your sample included subjects not in that population, i.e. males. Sampling bias results from using non-random sampling methods. Volunteer bias, when the sample consists of people who volunteer to participate, which might be different than the general population. Non-response bias, when those who participate in a study differ from those who did not respond. Response bias, when study participants either do not respond truthfully or give answers they feel the researcher wants to hear. For example, when students are asked if they ever cheated on an exam, even those who have would respond with no. Measurement or observation bias, systematic errors in measuring variables. Instrument bias, when a measuring instrument isn't calibrated correctly. Observer or examiner bias, when the person making the observation influences the results, either consciously or subconsciously. Additional reading. Types of bias, Kant. 5. Information or reporting bias occurs when participants do not provide accurate information. Recall bias, when individuals remember past events inaccurately. Response bias, the tendency for participants to respond in a certain way regardless of their true status or opinion. 6. Confounding bias, when an external factor, the confounder, affects both the independent and dependent variables, potentially producing a spurious association. 7. Publication bias, the inclination to publish results that are positive or show a significant finding and neglect non-significant or negative results. 8. Lead time bias, in medical screening, when early detection is confused with increased survival time, even though early detection might not impact the course of the disease. 9. Length time bias, in medical screening, where slow progressing cases are more likely to be detected than fast progressing cases. 10. Overfitting, in modeling, when a statistical model describes random error or noise instead of the underlying relationship, leading to overcomplicated models. 11. Bias due to omitted variables, when a model does not account for a variable that influences the outcome, leading to biased estimates. Understanding and identifying potential sources of bias is crucial in statistics to ensure the validity and reliability of findings. 1.3 Descriptive statistics. Major tasks in statistical analysis. Collecting data and analyzing data. Data collection, recording, sampling, and also including the planning of data collection in terms of the design of surveys and experiments. Data analysis, two main statistical methods: descriptive statistics, which summarizes data from a sample using indexes, example mean or standard deviation, and inferential statistics, which draws conclusions, prediction, from data that are subject to random variation. Assume we want to find average height of all grade 12 students in Canada. Population equals all grade 12 students in Canada. Parameter equals average height of all grade 12 students in Canada. We randomly select 200 grade 12 students in Canada and we measure height of all of them. Sample equals 200 grade 12 students that we selected. Sample statistic equals average height these 200 grade 12 students in Canada. Calculation of average height of these 200 students is descriptive statistics. Prediction of average height of all grade 12 students in Canada based on average of these 200 selected students is called inferential statistics. Prediction of population parameter based on sample statistic is called inferential statistics. Descriptive statistics. Descriptive statistics are statistics that quantitatively describe or summarize features of a collection of data, sample data set. Descriptive statistics are distinguished from inferential statistics, in that descriptive statistics aim to summarize a sample, rather than use the data to learn about the population that the sample of data is thought to represent. This generally means that descriptive statistics, unlike inferential statistics, are not developed on the basis of probability theory. Even when a data analysis draws its main conclusions using inferential statistics, descriptive statistics are generally also presented. Statistical inference is the process of making an estimate, prediction, or decision about a population based on sample data. Because population are almost always very large, investigating each member of the population would be impractical and expensive. It is far easier and cheaper to take a sample from the population of interest and obtain conclusions or make estimates about the population on the basis of information provided by the sample. However, such conclusions and estimates are not always going to be correct for various reasons. The results are very much depend on your samples. The critical step in the statistical process is the choosing of the sample. A badly chosen sample will result in poor predictions or estimates. To measure good or bad, we build into the statistical inference as the measure of reliability, such as confidence level and significance level in the further study. Hint: each test has some assumptions that sample data set must satisfy them, otherwise the prediction of that test is not reliable. The following measures are commonly used to describe the observations. A measure of location, or central tendency, such as the arithmetic mean, median, mode or interquartile. A measure of statistical dispersion, such as standard deviation, variance, range, interquartile range. A measure of the shape of the distribution, such as skewness or kurtosis. If more than one variable is measured, a measure of statistical dependence, such as the Pearson correlation coefficient, Spearman's correlation coefficient, and so on. When a population is believed to be normally distributed or close to normally distributed, parametric statistics is the best to be used. If not, it is best that a non-parametric method be used. Parametric statistics depend on normal distribution, but non-parametric statistics does not depend on normal distribution. Parametric statistics make more assumptions than non-parametric statistics. Parametric statistics use simpler formulae in comparison to non-parametric statistics. Most of the commonly known elementary statistic methods belong to parametric statistics. Non-parametric statistics is sparingly used and applied for special cases. I will talk about parametric and non-parametric in part 3 of this course. Exploratory data analysis, EDA, a preliminary approach to analyzing data that focuses on visualizing, summarizing, and understanding its main characteristics and underlying patterns. The goal of EDA is to uncover relationships, anomalies, and insights within the data to inform further analysis and decision-making. Key components and techniques of EDA include visualization, using various graphs and charts like histograms, scatter plots, box plots, and more to visually explore the data. Visualization aids in identifying patterns, outliers, and relationships between variables. Summary statistics, computing statistics like mean, median, mode, standard deviation, and quantiles to get a sense of the distribution and spread of the data. Handling missing values, identifying and treating missing data. Decisions might involve filling them with a certain value, example mean, median, or removing them. Identifying outliers, detecting and deciding how to handle outliers, which are extreme values that deviate from other observations. Checking for duplicates, ensuring that the data doesn't have unwanted duplicate rows or values. Correlation analysis, checking how different variables correlate with each other. This can assist in feature selection for machine learning models and understanding relationships. Dimensionality reduction, if the dataset is vast with many variables, techniques like PCA, principal component analysis, can be used to reduce the number of variables without losing much information. Distribution analysis, examining the distribution of the data, like checking for normality or other distribution forms, to understand its spread and shape. Through these techniques, EDA provides a comprehensive understanding of the dataset, helping analysts and data scientists make informed decisions about subsequent steps in the data analysis process. What is exploratory data analysis in simple word? American mathematician John Tukey promoted the use of EDA in his book, Exploratory Data Analysis, Pearson. Tukey emphasized that analysts need first to explore the data for potential research questions before jumping into confirming the answers with hypothesis testing and inferential statistics. EDA is often likened to interviewing the data. It's a time for the analyst to get to know it and learn about what interesting things it has to say. As part of our interview, we'll want to do the following. Classify our variables as continuous, categorical, and so forth. Summarize our variables using descriptive statistics. Visualize our variables using charts. The first step in any data science project, exploring the data. Exploratory data analysis, or EDA, is a comparatively new area of statistics. EDA focuses more narrowly on checking assumptions required for model fitting and hypothesis testing, and handling missing values, detecting outliers, and making transformations of variables as needed. Stuff done during EDA. Trends. Distributions. Mean. Median. Outliers. Variance. Correlations. Hypothesis testing. Visual explorations. EDA is a process to try to understand existing data by visualization, summarization, and testing hypotheses. Descriptive statistics cont. Key terms for rectangular data. Structured data vs unstructured data. Types of variables. Break. Univariate analysis for qualitative variables. Classroom exercise. Qualitative, categorical. Data that serves the function of a name only. Categorical values may be ordinal, where the names imply levels with hierarchy or order of preference, possible to apply rank order, i.e. a clear ordering to its categories, e.g. level of education, day of the week. Nominal, where no hierarchy is implied, e.g. purpose of loan, weather, eye color. Binary, where there are two choices, e.g. male and female, yes and no, 0 and 1. For example, for coding purposes, you may assign male as 0, female as 1. The numbers 0 and 1 stand only for the two categories and there is no order between them. Note, a binary attribute is a special case of a nominal attribute. The best way to summarize categorical data is to use frequencies and percentages like in the table. How can one graph qualitative variables? Two common choices are the pie chart and the bar chart. Pie charts may not be suitable for too many categories. Thus, if there are too many categories, you can either combine some categories or use a bar chart to represent the data. What is meant by too many? There is no clear cutoff, more of just a judgment on the appearance. Bar graph vs pie graph, when to use what? Generally, you should use a bar graph when you want to compare values between different categories or groups, and a pie graph when you want to show the relative sizes of the different parts of a whole. They are the most useful when you are analyzing a small number of categories or parts that add up to a whole, one, and mutually exclusive. However, pie graph should not be preferred more than 6 to 7 categories, as viewers may not be able to differentiate among them immediately. For example, if you have conversion rate for 3 different approach conversion rate A 5.6%, B 4.2%, C 5.2%, we can't use pie chart since they are not part of the whole and they are not mutually exclusive. Mutually exclusive is a term used to describe a situation in which 2 or more events or categories cannot occur simultaneously. In other words, when events or categories are mutually exclusive, the occurrence of one event or belonging to one category precludes the occurrence or membership of the others in the same context. For example, if you have a set of categories A, B, and C, and they are mutually exclusive, it means that if an item or event falls into category A, it cannot simultaneously fall into categories B or C. These categories do not overlap in the context you are considering. In statistics and probability theory, the concept of mutually exclusive events is important for calculating probabilities, especially when dealing with events that cannot happen at the same time. For example, when rolling a standard 6-sided die, the events of getting a 1, 2, 3, 4, 5, or 6 are mutually exclusive because only one of these outcomes can occur in a single roll. In a pie chart, the entire circle represents 100% of a whole, and each slice of the pie represents a portion or category of that whole. The sizes of the slices are relative to their proportions of the whole. For example, in a pie chart showing the distribution of a budget, each category represents a portion of the total budget, and the whole budget is 100%. In the case of conversion rates for different approaches, there is no whole to represent as a sum of parts. Each approach's conversion rate is an independent percentage, and there is no combined or total percentage that makes up a whole. Not mutually exclusive events or categories cannot occur simultaneously. In a pie chart, the assumption is that each category is mutually exclusive, an item can belong to only one category. For example, in a pie chart showing the sources of website traffic, example organic search, direct, referral, each visit is attributed to one and only one source. In the context of conversion rates for different approaches, there is no exclusivity requirement. An individual or event could potentially be associated with multiple approaches simultaneously. For example, a website visitor might be exposed to both approach A and approach B, and their conversion may be influenced by both. This lack of mutual exclusivity makes a pie chart an inappropriate choice for visualizing the data. Measures of central tendency, also known as measures of location, are typically among the first statistics computed for the continuous variables in a new data set. The main purpose of computing measures of central tendency is to give you an idea of what a typical or common value for a given variable is. The 3 most common measures of central tendency are the mean, the median, and the mode. While measures of central tendency are important, they do not tell the whole story. For example, suppose the mean score on a statistics exam is 80%. From this information, can we determine a range in which most people scored? The answer is no. There are 2 other types of measures of position and variability, that help paint a more concise picture of what is going on in the data. In this section, we will consider the measures of position and discuss measures of variability in the next one. Measures of position give a range where a certain percentage of the data fall. The measures we consider here are percentiles and quartiles. The 5-number summary of a data set consists of the minimum, maximum, and quartiles written in increasing order: min, Q1, Q2, Q3, max. There are several methods for finding percentile, and the result of them are a little difference. The previous method that I used is called MNM method. Example: consider the following data set with 13 observations. 1, 2, 3, 5, 7, 8, 11, 12, 13, 15, 18, 18, 20. First, we have to sort the data, but it is already sorted. We want to find the 25th percentile, so p equals 25. We have 13 observations, so n equals 13. R equals / equals 0.25 asterisk 13 equals 3.25, which is not an integer, so we will use the second option, number 3 in the preceding list, dot. If it was 3 we had to get average between 3rd and 4th OBS, but since it not integer we are calculating xceling of that for finding location of 25th percentile. Since xceling of 3.25 is 4, the 25th percentile is th 4th observation, which has the value 5. We can follow the same steps to find the 75th percentile. 7 / equals 0.75 asterisk 13 equals 9.75, not an integer. 8 xceling of 9.75 is 10. Therefore, the 75th percentile is the 10th observation, which has the value 15. Therefore, the interquartile range is 15, 5, or 10. The resistance of the interquartile range to outliers should be clear. This data set has a range of 19, 21, and an interquartile range of 10, however, if the last value was 200 instead of 20, 1, 2, 3, 5, 7, 8, 11, 12, 13, 15, 18, 18, 200, the range would be 199, 201, but the interquartile range would still be 10, and that number would better represent most of the values in the data set. E.g., a sample with 10 OBS, 21, 31, 42, 5, 5, 9, 10, 220, 70, 67 find 25th, 30th, 50th and 75th percentile. After sorting the data, 5, 5, 9, 10, 21, 31, 42, 67, 70, 220. 25%, _1, location R equals 25 / 100, 10 plus 1, equals 0.25 11 equals 2.75, 2.75 is the location of _1 after sorting data from smallest to largest, so it is located between second and third OBS more close to third one. That means _1 equals value of second observation, after sorting ascending, plus 0.75 asterisk, value of third OBS. Value of second OBS. _1 equals 5 plus 0.75, 9 to 5, equals 5 plus 0.75 asterisk 4 equals 8. Find 30th percentile. R equals 30 / 100, asterisk, 10 plus 1, equals 3.3, that means 30th percentile located between 3rd OBS and 4th OBS, so value of it equals value of 3rd OBS plus 0.3, value of 4th OBS, value of 3rd OBS. Value of 30% percentile equals 9 plus 0.3, 10 to 9, equals 9 plus 0.3 equals 9.3. Median equals _2 equals 50th percentile. Location of _2 equals 50 / 100, asterisk, 10 plus 1, equals 5.5. _2 equals 21 plus 0.5, 31 to 21, or 21 plus 31, / 2 equals 26. _3 equals 75% equals. Location of _3 equals R equals 0.75 asterisk, 10 plus 1, equals 8.25. _3 equals 67 plus 0.25, 70 to 67, equals 67 plus 0.75 equals 67.75. So for this data set the 5 number summary is men equals 5, _1 equals 8, _2 equals 26, _3 equals 67.75, max equals 220. As you saw, there are 3 quartiles in a set of numbers. The lower quartile Q1. The middle quartile, called the median, Q2. The upper quartile Q3. The quartiles divide the set, when they are in numerical order, into 4 equal groups. There are different methods for finding the quartiles, which give different values for them. So different software packages will produce different results. In SAS, you can use the PLDEF equals option in PROC univariate or the CTLDEF equals option in other procedures to control the method used to estimate quantiles. Note, within each method, the method is slightly different dependent on whether there are an odd or even number of numbers in the set. Our statistical software, excellent, and free from www.r-project.org, gives you a choice of 9 different algorithms. Here are some sample printouts from my example above. Some types insist on giving only exact sample values as quartiles, others can pick values between sample values. If you have access to R, and are curious to pursue this further, you could look at the R help screen at quantile undertype. But as a beginning statistician, you might do better just to understand that these differences do exist and decide not to worry much about them. Follow the rule in your textbook and expect your calculator or software to give different answers sometimes. Fortunately, in practice, quantiles are most often used for very large data sets. And for large data sets, differences among algorithms become less noticeable and are often unimportant. A helpful summary of the data is called the 5-number summary. The 5-number summary consists of 5 values. The minimum, the lower quartile, Q1, the median, also known as Q2, the upper quartile, Q3, the maximum. Example: SAS 98, 98, 97, 95, 94. Python 98, 96, 95, 94, 93. You are a new student in which course? If you got 96, you did well? Answer: you have to find in each course your rank is better. So you have to order data. Descending. SAS 98, 98, 97, 95, 94. Python 98, 96, 95, 94, 93. In Python your rank with 96 is better. After ordering data. Python 98, 96, 96, 95, 94, 93. You are the second student in Python. SAS 98, 98, 97, 96, 95, 94. You are the fourth student in SAS. Measures of variability. Dispersion refers to how variable or spread out data values are. For this reason, measures of dispersions are sometimes called measures of variability or measures of spread. There are many ways to describe variability or spread, including range, interquartile range, IQR, variance and standard deviation. Range. The range is the difference in the maximum and minimum values of a data set. The maximum is the largest value in the dataset and the minimum is the smallest value. The range is easy to calculate, but it is very much affected by extreme values. Range equals maximum minimum. E.g. 5, 5, 5, 5, 5, 5, 5, 5, mean equals 5, median equals 5, min equals 5, max equals 5, range equals 5-5 equals 0. 0, 1, 2, 5, 8, 9, 10, mean equals 5, median equals 5, min equals 0, max equals 1, 0, range equals 10-0 equals 10. Interquartile range, IQR. The interquartile range is the difference between upper and lower quartiles and denoted as IQR. IQR equals Q3, Q1 equals upper quartile, lower quartile equals 75th percentile, 25th percentile. Note: the IQR is not affected by extreme values, outliers. The most common measures of dispersion for continuous data are the variance and standard deviation. Both describe how much the individual values in a data set vary from the mean or average value. The variance and standard deviation are calculated slightly differently depending on whether a population or a sample is being studied, but basically the variance is the average of the squared deviations from the mean, and the standard deviation is the square root of the variance. Unbiased and biased estimators. We want our estimator to match our parameter, in the long run. In more precise language, we want the expected value of our statistic to equal the parameter. If this is the case, then we say that our statistic is an unbiased estimator of the parameter. If an estimator is not an unbiased estimator, then it is a biased estimator. In calculating the variance, we have changed from our original units to squared units, which might not be convenient to interpret. For instance, if we were measuring weight in pounds, we would probably want measures of central tendency and dispersion expressed in the same units rather than having the mean expressed in pounds and variance in squared pounds. To get back to the original units, we take the square root of the variance. This is called the standard deviation and is signified by sigma for a population and s for a sample. The CV cannot be calculated if the mean of the data is 0, because you cannot divide by 0, and is most useful when the variable in question has only positive values. If a variable has both positive and negative values, the mean can be close to 0, although the data actually has quite a broad range, and this can produce a misleading CV value because the denominator will be a small number, potentially producing a large CV value even if the standard deviation is fairly moderate. Descriptive statistics Cont. 1. Visualization. 2. Computing descriptive statistics using Excel. 3. Concepts of distribution and shape of data, frequency, quintiles, and outliers. 4. Different kinds of distribution, shape, and attributes. 5. Chebyshev's rule. 6. Empirical rule. If there are many data points and we would like to see the distribution of the data, we can represent the data by a frequency histogram or a relative frequency histogram. A histogram looks similar to a bar chart, but it is for quantitative data. In other words, a histogram is a graphical display of data using bars of different, for example, annual income. There is no order in x-axis for vertical bar chart. For horizontal bar chart there is no order in y-axis. In histogram usually, there is no space between adjacent bars, but we are using bar chart to display qualitative variable graphically, and there is space between adjacent bars and there is no order for x-axis. To create a histogram, the data need to be grouped into class intervals. Then create a tally to show the frequency, or relative frequency, of the data into each interval. The relative frequency is the frequency in a particular class divided by the total number of observations. In histogram the bars are as wide as the class interval and as tall as the frequency, or relative frequency. To obtain useful information and find the pattern of the above data more easily, we can create the frequency distribution tables from the data. What is it and how to do it? Define variable x, random, the numbers of children in a family. In this data set, we can see x took values 0 to 7, then list x in a table. From the above table, we can see sum of all the frequency is 25, which indicated all the data in. Max frequency is 6, min frequency is 1. How many family have 7 children? Only 1. 6 families have 2 children. Family tend to have 0 to 4 children. Draw x horizontal line and y vertical line. Point in x represent the number of children. Point in y represent the frequency. Then draw the bar with the x point in the middle. The height of the bar is the frequency for that number of children. Dividing the total population / sample to different groups that doesn't have any intersection is called segmentation or binning. Division of the total market into smaller, relatively homogeneous groups. As an example, a box plot, also called a box and whisker diagram, is based on the 5-number summary, can be used to provide a graphical display of the center and variation of a dataset. To create this plot we need the 5-number summary. Therefore, we need minimum value, Q1, lower quartile, Q2, median, Q3, upper quartile, and maximum value. Using the 5-number summary, one can construct a skeletal box plot. Mark the 5-number summary above the horizontal axis with vertical lines. Connect Q1, Q2, Q3 to form a box, then connect the box to min and max with a line to form the whisker. Most statistical software does not create graphs of a skeletal box plot but instead opt for the box plot as follows below. Box plots from statistical software are more detailed than skeletal box plots because they also show outliers. However, if there are no outliers, what is produced by the software is essentially the skeletal box plot. The following terminology will prepare us to understand and draw this more detailed type of the box plot. Potential outliers are observations that lie outside the lower and upper limits. Lower limit equals Q1, 1.5 IQR. Upper limit equals Q3 plus 1.5 IQR. Adjacent values are the most extreme values that are not potential outliers. So the smallest value and largest value that they are not potential outliers are adjacent values. Find Q1, Q2, and Q3 and connect Q1, Q2, Q3 to form a box, then find lower inner fence equals lower limit equals Q1 1.5 IQR. Upper inner fence equals upper limit equals Q3 plus 1.5 IQR. Then find potential outliers. If the value is less than Q1-1.5 IQR or bigger than Q3 plus 1.5 IQR, it is potential outliers. Find adjacent values, the largest and smallest values that they are not potential outliers. Then connect the box to the adjacent values with a line to form the whisker. Connect Q1, Q2, Q3 to form a box, then calculate. Lower limit equals Q1, 1.5 IQR. Upper limit equals Q3 plus 1.5 IQR. Any value less than lower limit equals Q1, 1.5 IQR or bigger than upper limit equals Q3 plus 1.5 IQR called potential outliers. Then to draw a left whisker we connect the box with the smallest value in data that is not potential outliers, and to draw a right whisker we connect the box with the largest value in our data that is not potential outliers. Sort your data, rank the observations from smallest to largest. If r equals / is an integer, a round number with no decimal or fractional part, the pth percentile of the observations is the average of rth observation and the next one. Average the / th and /+1 th. If r equals / is not an integer, the pth percentile of the observation is the r+1 equals selling of r. j+1 th largest measurement, where j is the largest integer less than /. Calculate the interquartile range as the difference between the 75th and 25th percentile measurements. As an example, if /100 equals 4.26 pth percentile is 5th OBS in sorted data. If /100 equals 12.676 pth percentile is 13th OBS in sorted data. If /100 equals 14.5 pth percentile is 15th OBS in sorted data. If /100 equals 4 pth percentile is the average of 4th and 5th OBS in sorted data. If /100 equals 12 pth percentile is the average of 12th and 13th OBS in sorted data. Answer. Order your data, 42, 45, 45, 56, 56, 67, 87, 89, 900. Min equals 42, max equals 900, n equals 9. M&M method. 9 plus 1, /2 equals 5. The 5th OBS is median 42, 45, 45, 56, 56, 67, 87, 89, 900. Q1 equals the median of lowest half, median is excluded, Q1 equals 45 plus 45, /2 equals 45. Q3 equals the median of upper half, median is excluded, Q3 equals 87 plus 89, /2 equals 88. Method number 2, Q1 equals 25th percentile 0.25 asterisk, 9, equals 2.25. The position of _1 equals the selling of 2.25 equals 2.25 plus 1 equals 3. Q1 equals 3 RD OBS equals 45. Q2 equals 50 th percentile 0.5 asterisk 9 equals 4.5. Q2 equals 5 th OBS equals 56. Q3 equals 75 th percentile 0.75 asterisk 9 equals 6.75. The position of _3 equals the selling of 6.75 equals 6.75 plus 1 equals 7 equals _3 equals 7 th OBS equals 87. IQR equals _3 _1 equals 87. 45 equals 42. Lower limit equals _1 1.5, I equals 45 1.5, 42 equals -18. Upper limit equals _3 plus 1.5, I equals 87 plus 1.5, 42 equals 150. So any data less than lower limit or bigger than upper limit is potential outliers. 42, 45, 45, 56, 56, 67, 87, 89, 900. So box plot must contain all of data except outliers. 42 is the smallest value that is not outlier, and 89 is the largest value that is not outlier, so these two numbers called adjacent values. Example, please draw a box plot for following final exam score. 24, 58, 61, 67, 71, 73, 76, 79, 82, 83, 85, 87, 88, 88, 92, 93, 94, 97. Answer. First sort data, it is already sorted 24, 58, 61, 67, 71, 73, 76, 79, 82, 83, 85, 87, 88, 88, 92, 93, 94, 97. Murtaugh #1, MNM method, n equals 18, 18 plus 1, /2 equals 9.5. Median is the average of 9th OBS and 10th OBS. 24, 58, 61, 67, 71, 73, 76, 79, 82, 83, 85, 87, 88, 88, 92, 93, 94, 97. Q2 equals 82 plus 83, /2 equals 82.5. Q1 equals the median of lowest half, median is excluded, Q1 equals 71. Q3 equals the median of upper half, median is excluded, Q3 equals 88. Method number 2, Q1 equals 25th percentile 0.25 asterisk, 18, equals 4.5. The position of underscore 1 equals the selling of 4.5 equals 4.5 plus 1 equals 5. Q1 equals 5 THOBS equals 71. Q2 equals 50 th percentile 0.5 asterisk 18 equals 9. Q2 equals average of 9th OBS and 10th OBS equals 82 plus 83, slash 2 equals 82.5. Q3 equals 75 th percentile 0.75 asterisk, 18, equals 13.5. The position of underscore 3 equals the selling of 13.5 equals 13.5 plus 1 equals 14 equals underscore 3 equals 14 THOBS equals 88. IQR equals underscore 3 underscore 1 equals 88. 71 equals 17. Lower limit equals underscore 1 1.5, I, equals 71 1.5, 17, equals 45.5. Upper limit equals underscore 3 plus 1.5, I, equals 88 plus 1.5, 17, equals 113.5. 24, 58, 61, 67, 71, 73, 76, 79, 82, 83, 85, 87, 88, 88, 92, 93, 94, 97. Method hashtag 3. Order data, 24, 58, 61, 67, 71, 73, 76, 79, 82, 83, 85, 87, 88, 88, 92, 93, 94, 97. N equals 18. Min 24 max 97. The position of Q1 equals 25/100, asterisk, 18 plus 1, equals 4.75. Q1 equals 67 plus 0.75, 71 to 67, equals 70. The position of Q2 equals 50/100, asterisk, 18 plus 1, equals 9.5. Q2 equals 82 plus 83, /2 equals 82.5. The position of Q3 equals 75/100, asterisk, 18 plus 1, equals 14.25. Q3 equals 88 plus 0.25, 92 to 88, equals 89. IQR equals Q3 Q1 equals 89-70 equals 19. Lower limit equals Q1 1.5 asterisk IQR equals 70, 1.5 asterisk 19 equals 41.5. Adjacent value equals 58 equals lower limit. Upper limit equals Q3 plus 1.5 IQR equals 89 plus 1.5 19 equals 117.5. Adjacent value equals 97. For numerical variables, the shape of the data helps us to determine the most appropriate measure of central tendency. The three most important descriptions of shape are symmetric, left skewed, and right skewed. Skewness is a measure of the degree of asymmetry of the distribution. Symmetric, mean, median, and mode are all the same here. No skewness is apparent. The distribution is described as symmetric. Left skewed or skewed left. Mean is located on the left side of mode and median is always between mean and mode. Mean. Right skewed or skewed right. Mean is located on the right side of mode. And median is always between mean and mode. Mode. So for left skewed, mean is located on the left side of mode, and for right skewed is located on the right side of mode. Median is always located between mean and mode. Note: when one has very skewed data, it is better to use the median as measure of central tendency since the median is not much affected by extreme values. Project requirements. Select a dataset that contains a minimum of 500 entries and at least 5 distinct types of data, encompassing both numerical and categorical variables. Undertake an exploratory data analysis, EDA, by formulating at least 10 investigative questions and seeking their answers. Conduct a univariate analysis on the target variable and a minimum of 4 other features, incorporating appropriate visualizations to support your analysis. Perform a bivariate analysis contrasting the target variable against at least 4 other features, again supporting your findings with visual diagrams. Your EDA should comprehensively include both Spearman's and Pearson's correlation assessments, along with the chi-square test, t-test, and ANOVA. Submission requirements include a PowerPoint presentation, a detailed report of your findings, the SAS code utilized for analysis, The dataset you based your analysis on. The due date for these items is December 4th. You will have 8 minutes to present your findings, followed by a 2-minute session for questions and answers. Your presentation should begin with an introduction that outlines the dataset structure, the variables included, the business issue at hand, and your initial hypotheses. It should cover at least 2 aspects of both univariate and bivariate analyses with visual aids, and include your findings on correlation, the chi-square test, the t-test, and ANOVA. Conclude with your overall conclusions and recommendations. Your written report must include a comprehensive introduction detailing the dataset structure, the variables present, the business challenge addressed, and your hypotheses. It should also provide answers to all 10 questions posed, followed by a conclusion and recommendations based on your analysis. 5.1 Test. 5.2 Univariate analysis using SAS. Univariate analysis for qualitative variables using SAS. Break. Univariate analysis for quantitative variables using SAS. 5.3 Probability. Interpretations of probability. Properties of probability. Utilize the Day 5 of FDAS.SAS code to enhance your skills in the following areas. Univariate analysis for qualitative variables using SAS. Univariate analysis for quantitative variables using SAS. Up to this point, we have been concentrating on descriptive statistics, methods for organizing and summarizing data. Next step is to present the fundamentals of inferential statistics, which is the methods of drawing conclusions about a population based on information obtained from a random sample of the population. Uncertainty is inherent in inferential statistics because we can never be certain that our conclusions are correct. So before we can understand, develop, and apply the methods of inferential statistics, we need to become familiar with uncertainty. The science of uncertainty is called probability theory. Probability theory enables us to evaluate and control the likelihood that a statistical inference is correct. Experiment, this refers to an action, the result of which is uncertain, for example, tossing a coin. Event, this refers to a single outcome of an experiment, for example, tossing a coin and getting heads. Sample space, the total number of possible outcomes of an experiment make up the sample space. It is mathematically represented as omega. For example, in a single coin toss, omega equals heads, tails. Example, suppose we randomly select a group of students and ask them how many pairs of jeans do you own. In this case, all possible outcomes are sample space equals 0, 1, 2, 3, 4. Some of the events can be defined as: A is the event that a randomly selected student owns no jeans. A equals 0. B is the event that a randomly selected student owns at least one gene. B equals 1, 2, 3, 4. The classical approach, if the outcomes in the sample space are equally likely, the probability of event A is, where n, A, is the number of elements in the event A, and n, S, is the number of elements in the sample space S. Example, when you roll a die. 1. Sample space. 2. A is an event that outcome is less than 3. 3. B is an event that outcome is bigger than 3. 4. C is an event that outcome is equal to 3. 5. D is an event that outcome is even number. 6. E is an event that outcome is odd number. 7. F is an event that outcome is less than 8. 8. G is an event that outcome is bigger than 8. Example, when you roll a die. Sample space, S equals 1, 2, 3, 4, 5, 6. A is an event that outcome is less than 3, A equals 1, 2 P, A, equals 2/6 equals 1/3. B is an event that outcome is bigger than 3, B equals 4, 5, 6 P, B, equals 3/6 equals 1/2. C is an event that outcome is equal to 3, C equals 3P, C, equals 1/6. D is an event that outcome is even number, D equals 2, 4, 6 P, D, equals 3/6 equals 1/2. E is an event that outcome is odd number, E equals 1, 3, 5 P, E, equals 3/6 equals 1/2. F is an event that outcome is less than 8, F equals 1, 2, 3, 4, 5, 6 equals SP, F, equals P, S, equals 6/6 equals 1. G is an event that outcome is bigger than 8, G equals P, G, equals P, equals 0/6 equals 0. In the case of simple experiments like tossing a coin or rolling a die, it is important to assume that the experiments are fair, i.e., all outcomes are equally likely. However, most experiments in real life will be biased and have unequal outcomes. Solution for Day 6 homework. Random variables. 3. Probability distribution. 3.1 Discrete probability distribution. Expected value, or mean, of a discrete random variable. Variance of a discrete random variable. Binary, Bernoulli, distribution. Binomial distribution. Distributions and statistical tests. Random variables. A random variable is a variable whose value depends on possible outcomes. Let us throw the die 10 times, the outcome of results may be 2 3 4 5 1 3, 6, 4 3 4. Let define the results as variable x. Variable x has data value as above. Variable x is a random sample of size 10 from population 1 to 6. X equals 1, 2, 3, 6. Let us throw the coin 10 times, the results may be HHTHTTHTHH. Let define the results as variable y. Variable y has data value as above. Variable y is a random variable. E.g. 1, let us throw the coin 2 times, the sample space is S equals HHHTTHTT. Let define variable x. Number of heads. X is a random variable, x equals 0, 1, 2. X, HH, equals 2. X, HT, equals 1. X, TH, equals 1. X, TT, equals 0. X, HHHTTHTT 0, 1, 2. E.g. 2, let us throw the coin 3 times, the sample space is S equals HHHHHT, TTT. Let define variable x. Number of heads. X is a random variable, x equals 0, 1, 2, 3. S equals HHHHHT, TTT. X equals 0, 1, 2, 3. As you can see, by defining random variable, we converted sample space to a subset of real numbers. E.g. 3, let us throw the die 2 times. S equals 1, 1, 1, 2, 6, 6. Let define variable y. Sum of the results. Y equals 2, 3, 4, 5, 12. S equals 1, 1, 1, 2, 6, 6. Y equals 2, 3, 4, 5, 12. E.g. 3, let assume families with 3 children. S equals BBBBBG, GGG. Let define variable x. Number of boys they have. S equals BBBBBG, GGG. X equals 0, 1, 2, 3. Variable, we converted sample space to a subset of real numbers. E.g. 1, let us throw the coin 2 times, the sample space is S equals HHHTTHTT. Let define variable x. Number of heads. X is a random variable, x equals 0, 1, 2. X, HH, equals 2. X, HT, equals 1. X, TH, equals 1. X, TT, equals 0. X, HHHTTHTT 0, 1, 2. As you can see here, by defining random variable, we converted sample space to a subset of real numbers. E.g. 2, let us throw the coin 3 times, the sample space is S equals HHHHHT, TTT. Let define variable x. Number of heads. X is a random variable, x equals 0, 1, 2, 3. S equals HHHHHT, TTT. X equals 0, 1, 2, 3. As you can see, by defining random variable, we converted sample space to a subset of real numbers. E.g. 3, let us throw the die 2 times. S equals 1, 1, 1, 2, 6, 6. Let define variable y. Sum of the results. Y equals 2, 3, 4, 5, 12. S equals 1, 1, 1, 2, 6, 6. Y equals 2, 3, 4, 5, 12. E.g. 3, let assume families with 3 children. S equals BBBBBG, GGG. Let define variable x. Number of boys they have. S equals BBBBBG, GGG. X equals 0, 1, 2, 3. E.g. 5, let us throw a coin 4 times, the sample space is S equals HHHHHHT, TTTN, S, equals 16. Let define variable x number of heads. X is a random variable, x equals 0, 1, 2, 3, 4. E.g. 6, let assume families with 2 children. S equals, boy, 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 girl, girl, boy, girl, girl, and S equals 4. Let define variable x number of boys they have. S equals BBBGGBGG x equals 0, 1, 2. Note, in previous example, probability of boy, boy equals probability of boy, girl equals probability of girl, boy equals probability of girl, girl equals 1/4 equals 25%. But probability of x equals 0, p, x equals 0, equals p, no boy, equals p, gg, equals 1/4 equals 25%. Probability of x equals 1, p, x equals 1, equals p, 1 boy, equals p, bggb, equals 2/4 equals 50%. Probability of x equals 2, p, x equals 2, equals p, 2 boys, equals p, bb, equals 1/4 equals 25%. Types of random variables. There are 2 types of random variables, qualitative, or categorical, and quantitative, or numerical. Qualitative random variables. The possible values vary in kind but not in numerical degree. They are also called categorical variables. Quantitative random variables. There are 2 types of quantitative random variables. Discrete random variable, when the random variable can assume only a countable, sometimes infinite, number of values. Continuous random variable, when the random variable can assume an uncountable number of values in a line interval. As an example, if you throw a coin 4 times, and define variable x number of heads. X is a discrete random variable, x equals 0, 1, 2, 3, 4. But if you select a number between 0 and 1, this is continuous random variable. A random variable is something that is used to quantify outcomes. The possible values of a random variable are the numerical outcomes of a particular experiment. It is commonly denoted with x, UOA. A probability distribution is a table, graph, or an equation that links each outcome of a statistical experiment with its probability of occurrence. Probability distribution is nothing but the graph obtained when we plot the probability of all random variables, UOA. Usually, x represents the random variable x. P, x, represents the probability of x. P, x equals x, refers to the probability that the random variable x is equal to a particular value. Note on notation. We use capitalized letters to represent the random variables and lowercase for the specific values of the variable. Definition of probability distribution. For previous example, let assume families with 2 children. S equals, boy, 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 girl, girl, boy, girl, girl, equals BBBGGBGGN, S, equals 4. Let define variable x number of boys they have. S equals BBBGGBGG x equals 0, 1, 2. P, x equals 0, equals probability of x equals 0 p, no boy, equals p, gg, equals 1/4 equals 25%. P, x equals 1, equals probability of x equals 1, p, 1 boy, equals p, bggb, equals 2/4 equals 50%. P, x equals 2, equals probability of x equals 2, p, 2 boys, equals p, bb, equals 1/4 equals 25%. There are 2 classes of probability functions. Probability mass functions, PMF, for discrete random variable, and probability density functions, PDF, for continuous random variable. Probability mass function, PMF. If the random variable is a discrete random variable, the probability function is usually called the probability mass function, PMF. If x is discrete, then, equals, x equals dot. In other words, the PMF for a constant, is the probability that the random variable x is equal to The PMF can be in the form of an equation or it can be in the form of a table. In previous example f, 1, equals p, x equals 1, equals p, 1 boy, equals 0.5 equals 50%. Properties of probability mass functions. 1, f, x, greater than or equal to 0 f, x, 0 for x in the sample space and 0 otherwise. 2, sigma f, x, equals 1. In other words, the sum of all the probabilities of all the possible outcomes of an experiment is equal to 1. Probability density function, PDF. If the random variable is a continuous random variable, the probability function is usually called the probability density function, PDF. Contrary to the discrete case, f, x, is not equal to p, x equals x. Properties of a probability density function. 1, f, x, greater than or equal to 0 f, x, 0 for x in the sample space and 0 otherwise. 2, the area under the curve is equal to 1. Cumulative distribution function, CDF. A cumulative distribution function, CDF, usually denoted f, x, is a function that gives the probability that the random variable, x, is less than or equal to the value x. F, x, equals p, x less than or equal to x. In previous example, f, 0, equals p, x less than or equal to 0, equals 0.25. F, 1, equals p, x less than or equal to 1, equals 0.25 plus 0.5 equals 0.75. F, 2, equals p, x less than or equal to 2, equals 0.25 plus 0.5 plus 0.25 equals 1. Note: the definition of the cumulative distribution function is the same for a discrete random variable or a continuous random variable. For a continuous random variable, however, p, x equals 0. Therefore, the CDF, f, x, equals p, x less than or equal to x, equals p, x. P, x equals 1.3, equals 0, 1/infinity equals 0. F, 1.3, equals p, x less than or equal to 1.3, equals p, x. Discrete and continuous. Discrete, possible values of finite or countable infinite numbers, for example number of boys in a family with 3 children. Continuous, possible values of interval or uncountable numbers, for example average height of children in a family with 3 children. Correspondingly, most probability distributions can be classified. Discrete probability distributions. Continuous probability distributions. One of the most important discrete random variables is the binomial distribution, and the most important continuous random variable is the normal distribution. For probability distribution, an important aspect of the distribution of a data set is its shape. There are some common distribution shapes: bell-shaped, triangular, uniform, right-skewed, left-skewed, bimodal, multimodal, reverse J-shaped, J-shaped. In considering the shape of a distribution, it is helpful to observe the number of peaks, highest points. Unimodal, a distribution has one peak. Bimodal, a distribution has two peaks may have different height. Multimodal, a distribution has 3 or more peaks. Technically, a distribution is bimodal or multimodal only if the peaks are the same height. However, in practice, distributions with pronounced but not necessarily equal height peaks are often referred to as bimodal or multimodal. Symmetry, the distribution can be divided into two pieces that are mirror images of one another, e.g. bell-shaped, normal, some triangular, rectangular, uniform, inverted U-shaped, etc. Bimodal and multimodal distributions sometimes are symmetry, but that are not always true. For the discrete probability distributions, only the most popular ones, Bernoulli and binomial probability distribution, are introduced in the following sections. For the continuous probability distributions, 4 distributions, uniform normal, t and chi_square distribution, are introduced in the following sections. Discrete probability distribution. A table, formula, or graph that lists all possible values a discrete random variable can assume, together with their associate probabilities. Requirements of discrete probability distribution. If a random variable x can take values _, then the following must be true. 0. In practice, probabilities assigned to values of a random variable are often estimated from relative frequencies from random samples, e.g. coin tossing 100 times or 200 times. Frequency distribution table to estimate the population probability distribution. Let us throw a coin 3 times, and define variable x number of heads. A. Please show probability distribution in table, graph, and equation. B. Please show cumulative probability distribution in table. As mentioned before, a cumulative probability refers to the probability that the value of a random variable falls within a specified range. Q. What is the probability that the coin flips would be in one or fewer tails? P. X less than or equal to 1, equals P, X equals 0, plus P, X equals 1, equals 0.25 plus 0.5 equals 0.75. A cumulative probability distribution can be represented by the following table. So the weighted average of possible values of a random variable, with weights given by their respective theoretical probabilities, is known as the expected value, usually represented by E, X. As an example, if we assume families with 2 children and define random variable number of boys, the mean of a discrete random variable X, expected value, is defined by mu X equals E, X, equals sigma X asterisk P, X, or mu equals E, X, equals. The formula means that we multiply each value, underscore, in the support by its respective probability, pi or f, x, and then add them all together. It can be seen as an average value but weighted by the likelihood of the value. Expected value, or mean, of a discrete random variable. The expected value is the average value that one would expect to obtain for a random variable if an experiment was repeated an infinite number of times. Laws of expected value. If x and y are random variables and c is any constant, then E, c, equals c. E, cx, equals ce, x. E, x plus y, equals e, x, plus e, y. E, xy, equals e, x, e, y. 5, e, xy, equals e, x, e, y if x and y are independent. Variance of a discrete random variable. The variance of a discrete random variable is given by. The formula means that we take each value of underscore, subtract the expected value, square that value and multiply that value by its probability. Then sum of all those values. There is an easier form of this formula we can use. Var, x, equals sigma 128, underscore, caret 2, underscore, equals sigma 128 underscore caret 2, underscore, caret 2 equals, caret 2, caret 2. The formula means that first, we sum the square of each value times its probability, then subtract the square of the mean. We will use this form of the formula in all of our examples. Standard deviation of a discrete random variable. The standard deviation of a random variable, x, is the square root of the variance. Laws of variance. If x and y are random variables and c is a constant, v, c, equals 0. 2, v, cx, equals c2v, x. 3, v, x plus c, equals v, x. 4, v, x plus y, equals v, x, plus v, y, if x and y are independent. V, xy, equals v, x, plus v, y, equals v, x, plus 1, caret 2v, y, equals v, x, plus v, y, if x and y are independent. Recall that a binary variable is a variable that has only two possible outcomes. For example, sex, male/female, or having a cancer, yes/no, are both examples of a binary categorical variable. A random variable can be transformed into a binary variable by defining a success and a failure. Usually, we show probability of success by P, and probability of failure by Q, so Q equals 1P, since sum of the probability of all possible outcomes is equal to 1, Q plus P equals 1, Q equals 1P. For example, if the probability of having cancer is 1%, P equals 0.01, the probability of not having cancer is 99%. Q equals 1P equals 1, 0.01 equals 0.99. Or consider rolling a fair 6-sided die and recording the value of the face. The random variable. Value of the face is not binary, x equals 1, 2, 3, 4, 5, 6. If we are interested, however, in the event a equals 6 is rolled, then the success is rolling a 6. The failure would be any value not equal to 6. Therefore, we can create a new variable with two outcomes, namely a equals 6 and b equals not a 6 equals 1, 2, 3, 4, 5. This new variable is now a binary variable. In this example, the probability of success, p, is 1/6 and probability of failure, q equals 1p, is 5/6. Or if we are interested, however, in the event a equals less than 3 is rolled, then the success is rolling a 1 0 R2. The failure would be any value bigger than 2. Therefore, we can create a new variable with two outcomes, namely a equals 1, 2 and b equals 3, 4, 5, 6. This new variable is now a binary variable. In this example, the probability of success, p, is 2/6 and probability of failure, q equals 1p, is 4/6. Expected value, variance, and standard deviation of binary, Bernoulli, distribution. Usually in binary, Bernoulli, distribution random variable is 0 or 1, 0 for failure and 1 for success. What is expected value, variance, and standard deviation for Bernoulli distribution? Failure x equals 0p, x equals 0, equals q. Success x equals 1p, x equals 1, equals p. So for Bernoulli distribution, expected value equals probability of success equals p. Variance equals probability of success asterisk probability of failure, equals caret 2 equals pq. Standard deviation equals square root of, probability of success asterisk probability of failure, sd equals square root. The binomial distribution is a special discrete distribution where there are two distinct complementary outcomes, a success and a failure. We have a binomial experiment if all of the following four conditions are satisfied. 1. The experiment consists of n identical trials. In previous example we had 3 trials. 2. Each trial results in one of the two outcomes, called success and failure. In previous example we had success, getting 6, and failure, not getting 6, in each trial. 3. The probability of success, denoted p, remains the same from trial to trial. In previous example probability of getting 6 in each trial is the same American Samoa 1/6. 4. The n trials are independent. That is, the outcome of any trial does not affect the outcome of the others. In previous example result of each trial was independent of other trials. Example, an FBI survey shows that about 80% of all property crimes go unsolved. Suppose that in your town 3 such crimes are committed, and they are each deemed independent of each other. What is the probability that one of 3 of these crimes will be solved? First, we must determine if the situation satisfies all 4 conditions of a binomial experiment. Does it satisfy a fixed number of trials? Yes, the number of trials is fixed at 3, n equals 3. Does it have only 2 outcomes? Yes, solved and unsolved. Do all the trials have the same probability of success? Yes, q equals 0.8, p equals 1, q equals 0.2. Are all crimes independent? Yes, stated in the description. To find the probability that only one of the 3 crimes will be solved, we first find the probability that one of the crimes would be solved. With 3 such events, crimes, there are 3 sequences in which only one is solved. P, SFF, equals P, solved first, unsolved second, unsolved third, equals 0.2, 0.8, 0.8, equals 0.128. P, FSF, equals P, unsolved first, solved second, unsolved third, equals 0.8, 0.2, 0.8, equals 0.128. P, FFS, equals P, unsolved first, unsolved second, solved third, equals 0.8, 0.8, 0.2, equals 0.128. We add these 3 probabilities up to get 0.384. Looking at this from a formula standpoint, we have 3 possible sequences, each involving 1 solved and 2 unsolved events. Putting this together gives us the following: 3, 0.2, 0.8, 0.8, equals 0.384 equals 3 at 1, 0.2, 0.8, 0.8, equals 3 at 1, 1, 1, equals 3 at 1, 1, caret 2. So for Bernoulli distribution, expected value equals probability of success equals p. Variance equals probability of success asterisk probability of failure, equals caret 2 equals pq. Standard deviation equals square root of, probability of success asterisk probability of failure, sd equals square root. For binomial distribution, Expected value equals n times of probability of success equals NP. Variance equals n times of probability of success asterisk probability of failure equals caret 2 equals NPQ. Standard deviation equals square root of n times of probability of success asterisk probability of failure SD equals square root n. Probability distribution cont. 3.2 Continuous probability distribution. Uniform distribution. The normal distribution. The standard normal distribution, Z distribution. If a random variable is a continuous variable, its probability distribution is called a continuous probability distribution. A continuous probability distribution differs from a discrete probability distribution in several ways. The probability that a continuous random variable will assume a particular value is 0. i.e. p, x equals 0 for any x. As an example, we randomly select any number between 1 and 2. The probability of getting exactly 1.3 equals to 0. A continuous probability distribution can't be expressed in tabular form. An equation or formula is used to describe a continuous probability distribution. The normal distribution is a family of continuous distributions that can model many histograms of real-life data which are mount-shaped, bell-shaped, and symmetric, for example, height, weight, etc. A normal curve has two parameters. Mean mu, center of the curve. Standard deviation sigma, spread about the center, or variance caret 2. The mean can be any real number and the standard deviation is greater than 0. The normal curve ranges from negative infinity to infinity. The image below shows the effect of the mean and standard deviation on the shape of the normal curve. N, 2,9, mu equals 2, variance equals caret 2 equals 9, standard deviation equals 3. N, 1,2, mu equals 1, caret 2 equals 2 equals square root 2. N, 0,1, mu equals 0, caret 2 equals 1 equals 1. The standard normal distribution. Z distribution. FYI. A random variable x with mean mu and standard deviation sigma is normally distributed if its probability density function is given by where x from negative infinite to positive infinite. It is sometimes referred to as a bell-shaped distribution. Hint, the term bell-shaped function or simply bell curve is used to describe the mathematical concept called normal distribution, sometimes referred to as Gaussian distribution. Bell curve refers to the bell shape that is created when a line is plotted using the data points for an item that meets the criteria of normal distribution. A special case of the normal distribution has mean mu equals 0 and a variance of caret 2 equals 1. The standard normal is an important distribution. A standard normal distribution has a mean of 0 and variance of 1. This is also known as a Z distribution. You may see the notation n, mu, caret 2, where n signifies that the distribution is normal, mu is the mean, and caret 2 is the variance. A Z distribution may be described as n, 0, 1. Note that since the standard deviation is the square root of the variance, then the standard deviation of the standard normal distribution is square root 1 equals 1. Standard score, Z, is usually used for normal distribution. The transformation from a raw score x to a z-score can be done using the following formula. Equals, slash. Transforming a variable in this way is called standardizing the variable. It should be kept in mind that if x is not normally distributed, then the transformed variable will not be normally distributed either. i.e., if you have a normal distribution and you need to calculate area under the curve, you can use this formula, equals, slash, to transform your data to z distribution and use z-table that gives you area under z distribution. Based on the definition of the probability density function, we know the area under the whole curve is 1. Since we are given the less than probabilities in the table, we can use complements to find the greater than probabilities. Therefore, p, z 0.87, equals 1p, z less than or equal to 0.87. Using the information from the last example, we have p, z 0.87, equals 1p, z less than or equal to 0.87, equals 1 0.8078 equals 0.1922. Percentiles of the standard normal distribution. Recall from part 1 that the PTH percentile is the value that is greater than or equal of p% of the values in a data set. For example, 30th percentile is a value that 30% of values are less than or equal to it. We can use the standard normal table or software to find percentiles for the standard normal distribution. The intersection of the columns and rows in the table gives the probability. If we look for a particular probability in the table, we could then find its corresponding z-value. Example, find the 10th percentile of the standard normal curve. The question is asking for a value to the left of which has an area of 0.1 under the standard normal curve. Since the entries in the standard normal cumulative probability table represent the probabilities and they are 4 decimal place numbers, we shall write 10% equals 0.10 as 0.1000 to remind ourselves that it corresponds to the inside entry of the table. We search the body of the tables and find that the closest value to 0.1000 is 0.1003. We look to the leftmost of the row and up to the top of the column to find the corresponding z-value. The corresponding z-value is minus 1.28. Thus z equals minus 1.28. Since we know that x have a normal distribution, equals 100 and equals 15, we can transform x distribution to z distribution by using following formula equals, slash, 0.30 equals 0.3000 z equals dash 0.52. 0.52 equals 100, slash 15x100 equals 15 asterisk, minus 0.52, equals dash 7.8 x equals dash 7.8 plus 100. X equals 92.2. Therefore 30% of people have a IQ less than or equal to 92.2. 30 percentile means 30% of the data less than 92.2 and 70% of the IQ IA more than 70%. 1 sampling distribution of the sample mean. 2 central limit theorem. 3 sampling distribution of the sample proportion. In inferential statistics, we want to use the characteristics of the sample, i.e. a statistic, to estimate the characteristics of the population, i.e. a parameter. Sampling distribution of the sample mean. Sampling distribution of the sample proportion. If we obtain a random sample and calculate a sample statistic from that sample, the sample statistic is a random variable, wow. The population parameters, however, are fixed. For example, let's assume the average height of all grade 12 students in Canada is 172.8 centimeters. So if we want to find average height of all grade 12 students in Canada, this number is population mean and it is parameter and the value of that is a fixed number, here 172.8 centimeters. Now if we randomly select 100 students from grade 12 in Canada to measure height of them and then calculate average of height of them, it is sample mean and it is statistic and value of that is changing from one sample to another sample I. Mean it could be 175.2 for one sample, 168.9 for another sample, and 171.4 for another sample. And so on, so the sample mean is random variable and it has its own distribution that we call it sampling distribution of the sample mean. The statistic is a random variable. Can we find the distribution? The mean? The standard deviation? The answer is yes. This is why we need to study the sampling distribution of statistics. So what is a sampling distribution? In this example, if you randomly select 100 students 50 times and calculate the average height of them, sample mean, this sample mean has its own distribution. Assume 15 of them have sample mean equals to 174.5, 16 of them have sample mean equals to 167.8, and 9 of them have sample mean equals to 181.2, and 8 of them have sample mean equals to 165.5 and 2 of them have sample mean equals to 185. So the above graph shows sampling distribution of the 50 sample means with size of 100. Sampling distribution. The sampling distribution of a statistic is a probability distribution based on a large number of samples of size n from a given population. Sampling distribution. The sampling distribution of a statistic is a probability distribution based on a large number of samples of size n from a given population. As you can see, population mean is a fixed number, equals 14, but sample mean depends on which 2 pumpkins are selected, so it is changing from one sample to another, and it is random variable. In following table I show you all possible outcomes for sample mean. The possible sample means cluster more closely around the population mean as the sample size increases. Thus, the possible sampling error decreases as sample size increases. For example, we want to find average height of all grade 12 students in Canada, so this number is population mean. And it is parameter and the value of that is a fixed number, assume it is 176 centimeters. If we randomly select 100 students, form grade 12 in Canada to measure height of them and then calculate average of height of them, it is sample mean. And assume we will get 178 centimeters, we have 2 centimeters error, 178-176 equals 2, if we randomly select 100 students again and calculate average height of them, it is sample mean and assume we will get 175 centimeters, we have -1 cm error, 175-176 equals 1, if we randomly select 100 students again and calculate average height of them, it is sample mean and assume we will get 174 centimeters, we have -2 cm error, 175-176 equals -2, until here the mean of sample mean equals to 178 plus 175 plus 174. 3 equals 175.66 cm. If you repeat this experiment over and over again, the mean of sample mean is going to very close to population mean, 176 centimeters. As you can see, by increasing sample size, standard error, standard deviation of sample mean tends to decrease. Sampling error. The error resulting from using a sample characteristic to estimate a population characteristic. Sample size and sampling error, the possible sample means cluster more closely around the population mean as the sample size increases. Thus, the possible sampling error decreases as sample size increases. If population is normal. If the population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of the sample mean is also normally distributed no matter what the sample size is, and you are allowed to find probability by converting it to z-description. Recall that when the sampling is done with replacement, or if the population size is large compared to the sample size, then has mean mu and standard deviation. We use the term standard error for the standard deviation of a statistic, and since sample average is a statistic, standard deviation of is also called standard error of. If population is normal. If the population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of the sample mean is also normally distributed no matter what the sample size is, and you are allowed to find probability by converting it to z-description. Recall that when the sampling is done with replacement, or if the population size is large compared to the sample size, then has mean mu and standard deviation. We use the term standard error for the standard deviation of a statistic, and since sample average is a statistic, standard deviation of is also called standard error of. The mean of the sampling distribution is very close to the population mean. The standard deviation of the sampling distribution is smaller than the standard deviation of the population, since it is equal to population standard deviation. Example: the engines made by Ford for speedboats have an average power of 220 horsepower, HP, and standard deviation of 15 HP. You can assume the distribution of power follows a normal distribution. Consumer Reports are testing the engines and will dispute the company's claim if the sample mean is less than 215 HP. If they take a sample of 4 engines, what is the probability the mean is less than 215? His central limit theorem applies to a sample mean from any distribution. We could have a left skewed or a right skewed distribution for population, but sample mean is approximately NORAMI distributed. As long as the sample size is large, the distribution of the sample means will follow an approximate normal distribution. For the purposes of this course, a sample size of n30 is considered a large sample. Central limit theorem. For a large sample size, we will explain this later, sample mean is approximately normally distributed, regardless of the distribution of the population one samples from. So if you know that your population is normal for any sample size, sample mean is normally distributed, and if your population is not normal but sample size is large enough, sample mean is normally distributed based on CLT, central limit theorem. Notes on the CLT for this demonstration. If the population is skewed and sample size small, then the sample mean won't be normal. If the population is normal, then the distribution of sample mean looks normal even if n equals 2. If the population is skewed, then the distribution of sample mean looks more and more normal. when n gets larger. So, the central limit theorem, CLT, states that the following properties hold true for any type of data as long as the number of samples is high. 1. Mean of a sampling distribution, x, equals mean of the population, mu. 2. Standard deviation of a sampling distribution, standard error, equals sigma slash square root n. 3. For n30, a sampling distribution becomes normally distributed. This property of sampling distributions is called the central limit theorem. Example. 1. For a given discrete random variable x, the population parameters are mu equals 5 and sigma equals 12. Now, if you take 10,000 sample means of size 100 from this population, what would the parameters of the distribution of sample means be? Mean equals 5 and standard error equals 1.2. 2. For a given continuous random variable y, the population parameters are mu equals 55 and sigma equals 1.8. What is the probability that a randomly chosen sample of size 36 will have a mean that lies between 54.7 and 55.3? According to the central limit theorem, the mean of the distribution of sample means, x, will be equal to the mean of the population, mu, and the standard error, se, will be sigma slash square root n, where n is the sample size. Hence, the mean is 55 and the standard error is 0.3 in this case. Now, 54.7 lies one standard error to the left and 55.3 lies one standard error to the right of the mean. Hence, p, 54.7. 3. For a given discrete random variable y, the population parameters are mu equals 30 and sigma equals 10.5. What is the probability that a randomly chosen sample of size 49 will have a mean that lies between 27 and 31.5? Metro College of Technology 28. For a given continuous random variable y, the population parameters are mu equals 55 and sigma equals 1.8. What is the probability that a randomly chosen sample of size 36 will have a mean that lies between 54.7 and 55.3? According to the central limit theorem, the mean of the distribution of sample means, x, will be equal to the mean of the population, mu, and the standard error, se, will be sigma slash square root n, where n is the sample size. Hence, the mean is 55 and the standard error is 0.3 in this case. Now, 54.7 lies one standard error to the left and 55.3 lies one standard error to the right of the mean. Hence, p, 54.7. 81.5, according to the central limit theorem, the mean of the distribution of sample means, x, will be equal to the mean of the population, mu, and the standard error, se, will be sigma slash square root n, where n is the sample size. Hence, mean is 30 and standard error is 10.5 slash square root 49 equals 10.5 slash 7 equals 1.5 in this case. Now, 27 lies 2 standard errors to the left of the mean and 31.5 lies 1 standard error to the right of the mean. Hence, p, 27. With the central limit theorem, we can finally define the sampling distribution of the sample mean. The sampling distribution of the sample mean will have the sample mean as the population mean, mu. Standard deviation standard error of se, spar, equals. It will be normal, or approximately normal, if either of these conditions is satisfied. The population distribution is normal. Or the sample size is large, greater than 30, so you can rely on CLT. Note as you increase the sample size, the standard error, i.e., the standard deviation of the sampling distribution, decrease. Example, the weights of baby giraffes are known to have a mean of population equals 125 pounds and a standard deviation of population of 15 pounds. If we obtained a random sample of n equals 40 baby giraffes, what is the probability that the sample mean will be between 120 and 130 pounds? What is the 75 percentile of the sample means of size n equals 40? The sampling distribution of the sample mean will have the sample mean as the population mean, mu. Standard deviation standard error of se, spar, equals. It will be normal, or approximately normal, if either of these conditions is satisfied. The population distribution is normal. Or The sample size is large, greater than 30, so you can rely on CLT. Whenever the population has a normal probability distribution, the sampling distribution of X is a normal probability distribution for any sample size. A population has a mean of 75 and a standard deviation of 8. A random sample of 800 is selected. The expected value of X is 75. Answer. Does the problem indicate that the distribution of weights is normal? No, it does not. In order to apply the central limit theorem, we need a large sample. Since n equals 40/30, we can use the theorem. The sampling distribution of the sample mean is approximately normal with mean mu equals 125 and standard error tau equals 15/40 equals 2.37. A. We want p, 120. Note, if we don't know the population standard deviation, instead of z distribution we should use t distribution that I will explain for you in this part. Note, if we don't know the population standard deviation, instead of z distribution we should use t distribution that I will explain for you in this part. Let me first start by reviewing a Bernoulli random variable, y. Bernoulli or binary random variable y. For an experiment that results in a success or a failure, let the random variable equal 1, if there is a success, and 0 if there is a failure. Therefore, y equals 1 success, 0 failure. And let p be the probability of a success. For example, in previous example blue is success, and because 2 of 5 children like blue, p equals 2. 5 equals 0.4 equals 40%. The Bernoulli random variable is a special case of the binomial random variable, where the number of trials is equal to 1. Suppose we have, say n, independent trials of this same experiment. Then we would have n values of y. Namely y1, y2, yn. If we define x to be the sum of those values, we get x equals y1 plus y2 plus yn. X is then a binomial random variable with parameters n and p. X is the number of success. For example, in previous example, when you chose a and b, y1 equals 0, y2 equals 1. X equals 0 plus 1 equals 1. Equals 1. 2. For binomial distribution, expected value equals n times of probability of success equals np. Variance equals n times of probability of success asterisk probability of failure equals 2 equals npq. Standard deviation equals square root of n times of probability of success asterisk probability of failure sd equals nq. We learned how to use the central limit theorem to find the sampling distribution for the sample mean and the sample proportion under certain conditions. We learned that the sampling distributions are centered around the population parameter with variability. All of this theory was built knowing the parameter. Can we use this information in situations where the parameter is unknown? The answer is yes. In the next lesson, we take our first step into inference and into the real world where the population parameters are unknown and need to be estimated. Introduction to inferences. Estimation and confidence intervals. Inference for the population proportion. Inference for the population mean. Students' t-distribution. Chi-square distribution. Statistical inference. The real power of statistics comes from applying the concepts of probability to situations where you have data but not necessarily the whole population. The results, called statistical inference, give you probability statements about the population of interest based on that set of data. Types of statistical inference. There are two types of statistical inferences, estimation and statistical tests. Estimation. Use information from the sample to estimate, or predict, the parameter of interest of population. For instance, using the result of a poll about the president's current approval rating to estimate, or predict, his or her true current approval rating nationwide. Statistical tests, hypothesis tests. Use information from the sample to determine whether a certain statement about the parameter of interest is true. Statistical tests are also referred to as hypothesis tests. For instance, suppose a news station claims that the president's current approval rating is more than 75%. We want to determine whether that statement is supported by the poll data. Estimation. Two common estimation methods are point and interval estimates. Point estimates An estimate for a parameter that is one numerical value. An example of a point estimate is the sample mean or the sample proportion. Note, point estimate of parameter is equal to value of sample statistic. Interval estimates. Interval estimates give an interval as the estimate for a parameter. This is a new concept which is the focus of this lesson. Such intervals are built around point estimates, which is why understanding point estimates is important to understanding interval estimates. In this course, the interval estimates we find are referred to as confidence intervals. Confidence interval. An interval of values computed from sample data that is likely to cover the true parameter of interest. The center of our interval should be the point estimate for the parameter of interest. E.g., a survey of the current approval rating of the president. In such surveys, you may hear reference to the 44% of those surveyed approved of the president's reaction. This is the sample proportion, and the survey had a 3.5% margin or error, or plus or minus 3.5%. This latter number is the margin of error. In this example, the point estimate is 44% and interval would be from 44% plus or minus 3.5%, i.e., 40.5% equals 44% dash 3.5%, to 47.5%, 44% plus 3.5%. In statistical inference we have two methods, point estimates and confidence interval. What is point estimates? In this method we get one single value as an output, one sample proportion and sample mean. What is confidence interval? It is range that the center point is sample mean or sample proportion. Assume we randomly selected 200 students from grade 12 in Canada and measured height of them and find that mean of height of them is 175 centimeters and with 95% confidence margin of error is 2 centimeters. So we can say 175 is sample statistic equals sample mean. Note, point estimate of parameter is equal to value of sample statistic. Average of height of all grade 12 students in Canada equals to 175 centimeters. This is a point estimate of average of height of all grade 12 students in Canada. Or we can say average of height of all grade 12 students in Canada is between 175 to 2, 175 plus 2, 173 centimeters and 177 centimeters, 175 plus or minus 2, this is interval estimate of average of height of all grade 12 students in Canada. Confidence interval equals interval estimate equals 173, 177. 173 plus 177, slash 2 equals 175 equals is your point estimate. In this case it is sample mean. The point estimate equals to sample mean and based on sample might be changed, so we need calculate margin of error. For finding margin of error based on we have to know confidence interval, sample standard deviation and sample size. I will show and prove its formula. Point estimates for a population mean. The point estimate of the population mean, mu, is equal to sample mean. Point estimate of the population mean equals sample mean. The notation that we are using for sample mean equals SPAR. The notation for population mean equals mu. Point estimate of the population proportion. The point estimate of the population proportion, P, is equal to sample proportion. Point estimate of the population proportion equals sample proportion. Sample proportion equals P. Population proportion equals confidence interval. Example, we measure the heights of 40 randomly chosen men, and get a mean height of 175 centimeters. We also know the standard deviation of men's heights is 20 centimeters. The 95% confidence interval, we show how to calculate it later, is 175 centimeters plus or minus 6.2 cm equals 168.8 cm 181.2 cm. Sample statistic equals 175 cm. Margin of error, ME, equals 6.2 cm. Claim, we are claiming that the mean height of population is 175 centimeters. 175-6.2, 175 plus 6.2, equals 168.8, 181.2. Confidence level is 95%. Confidence interval is 168.8, 181.2. Significance level or APHA 1-95% equals 0.05, the probability of rejecting null hypothesis in a test. We can say we are 95% confident that the true mean of all men, population mean, is between 168.8 centimeters and 181.2 centimeters. Mean equals 171, this one is belong to 95%. Mean equals 182, this one is belong to those 5%. But it might not be. The 95% says that 95% of experiments like we just did will include the true mean, but 5% won't. So there is a 195% equals 5% equals 5/100 equals 1/20, that our confidence interval does not include the true mean. In sampling distribution we are getting different samples from population. For some of the samples we are getting 175 centimeters as a mean, for some of them not. So here we can say in 95 vases we got 175, and for the rest of them Oregon in 5 cases we did not get 175 centimeters as a height mean. General format of a confidence interval. The center of our interval should be the point estimate for the parameter of interest. With the estimated standard error of the point estimate, we can include a measure of confidence to our estimate by forming a margin of error. Let us quickly get into the 4 terminologies that you just learned about. The probability associated with a claim is called the confidence level. The maximum error made in the sample mean is called the margin of error. The final interval of values is called the confidence interval. Significance level is estimated as significance level, alpha, equals 1, confidence level. Recall that the point estimate for population mean equals to sample mean, and based on sample might be changed, so we need calculate margin of error, and for finding margin of error based on what number you consider as your confident we must know sample standard deviation and sample size. I will show and prove its formula. And similar to it, that the point estimate for population proportion equals to sample proportion, and based on sample might be changed, so we need calculate margin of error, and for finding margin of error based on what number you consider as your confident we must know sample standard deviation and sample size. I will show and prove its formula. Note: some might say, why not just be 100% confident, but that does not make practical sense. For instance, what value comes from me saying I am 100% confident that the approval rating for the president is from 0% to 100%. That is the only interval in which one can be truly confident will capture the actual proportion. For 100% confident your range must include all possible outcomes. Similarly, if you were to ask your professor what they think your score I will be on an exam that has 20 marks total, and they reply, 0 to 20, what would you think of that answer? However, one does want to be as confident as reasonably possible. Most confidence levels use ranges from 90% confidence to 99% confidence, with 95% being the most widely used. In fact, when you read a report that includes a margin of error, you can usually assume this has a 95% confidence attached to it unless otherwise stated. If I say your mark is between 15 to 18 with 95% confident, that means there is 5% possibility that you will get less than 15 or more than 18. 1 alpha equals 0.95. Alpha equals 0.05. The value of the multiplier increases as the confidence level increases. This leads to wider intervals for higher confidence levels. We are more confident of catching the population value when we use a wider interval. When the confidence level is 0.95, what is the significancy level? Alpha equals 0.05. When the confidence level is 0.90, it is mostly used in cases we have less restrict, like lifestyle and health. When the confidence level is 0.98, it means that the significancy level is 0.02. This level mostly used in critical situation like trying new or novel surgery, because the interval will be narrower and it means we have much level of restrict. Commonly used alpha levels. Now we learned how to calculate multiplier for construction confidence level. As you know, for creating CL equals point estimate plus or me multiplier *SD. Point estimate, sample mean or sample proportion. Recall that if NP and N, 1P, are greater than 15, then is approximately normal with mean, P, standard error. So, Z equals, /1, /. Recall that if N greater than or equal to 30 or if X comes from a normal distribution with mean, mu, and variance, (2). Then the sampling distribution will be approximately normal with mean mu and standard error, SE, equals /. So when the population is normal or when the sample size is large enough, N greater than or equal to 30, then Z equals, /, where Z has a standard normal distribution. One way to estimate sigma is by S, the standard deviation of the sample, and replace sigma by S in the above Z equation. However, this new quotient no longer has a Z distribution. Instead, it has a T distribution. We call the following a studentized version of T equals / square root. So first you have to find out that is the population is known or unknown. For known population we must use Z distribution, for unknown population we must use T distribution. Now we learned how to calculate multiplier for construction confidence level. As you know, for creating CL equals point estimate plus or, me, multiplier asterisk SD. Point estimate, sample mean or sample proportion. Recall that if NP and N, 1P, are greater than 15, then is approximately normal with mean, P, standard error. So, Z equals, square root, 1, margin of error. So the population mean is a subset of sample mean plus minus margin of error. And margin of error depend on confident, standard deviation and sample size. By increasing confident, as an example using 98% confident instead of 95%. Underscore 2/2, underscore 1/2, the margin of error increase as well, so you will get wider interval. Multiplier for 0.95 equals 1.96. Multiplier for 0.98 equals 2.3261. Alpha equals 0.98. Alpha equals 0.02. What is underscore? Equals 0.01. If we increase sample size, margin of error decrease. By increasing population standard deviation, margin of error tends to be increased. If we want to estimate population mean with a single value, point estimate, we say population mean is 175 centimeters, but in this question, we want to find confidence interval. Step 1, start with the number of observations n, the sample mean, and the population standard deviation. Using our example, number of observations n equals 40. The sample mean equals 175. The population standard deviation equals 20. Interpret the confidence interval. We can say we are % confident that the population mean is between plus underscore / square root and underscore / square root. Point estimates for a population mean. The point estimate of the population mean, mu, is point estimate of the population mean equals sample mean. Point estimate of the population proportion. The point estimate of the population proportion, P, is point estimate of the population proportion equals sample proportion. Confidence interval for the population proportion. Check conditions. Check all conditions before using the sampling distribution of the sample proportion. We previously used NP and N, 1P. But P is not known. Therefore, for the confidence interval, we will use N greater than 15 and N, 1, 15. The general form of the confidence interval is the point estimate is the sample proportion, and the estimated standard error is. If the conditions are satisfied, then the sampling distribution is approximately normal. Therefore, the multiplier comes from the normal distribution. This interval is also known as the one sample Z interval for P, or the normal approximation confidence interval for P. We are using different name for this interval, one confidence interval 2. One sample Z interval for P3. Normal approximation confidence interval for P. Confidence interval for the population proportion, P. Where underscore 2 represents a Z value with alpha / 2 area to the right of it. General notes about the confidence interval. The plus or minus in the formula above means plus or minus. It is a shorthand way of writing. It is centered at the point estimate. The width of the interval is determined by the margin of error. You must determine the multiplier. Interpret the confidence interval applying the template from earlier in the lesson. We can say we are 1 alpha, 100% confident that the population proportion is between and or Z equals / n minus 1.96 minus 0.0251. We are 95% confident that the overall U.S. adult approval rating for the current president is from 41.5% to 46.5%. You could also see this written as, the current U.S. approval rating for the president is 44% with a 95% margin of error of 2.5%. Commonly, the standard level of confidence is 95%, so that reference is often left out, as that is the assumed level of confidence unless otherwise stated. Also, the method calculates a proportion, but often the reported values are converted to percentages. If you use the decimal formal, e.g. 0.415 and 0.465, then reference these as proportion and not percentage. Precision. The wider the interval, the poorer the precision. Note that the higher the confidence level, the wider the width, or equivalently, half width, of the interval, and thus the poorer the precision. For 100% confidence interval we must cover all of possible outcomes. Since the confidence level reflects the success rate of the method we use to get the confidence interval, we like to have a narrower interval while keeping the confidence level at a reasonably higher level. For most newspapers and magazine polls, it is understood that the margin of error is calculated for a 95% confidence interval, if not stated otherwise. A 3% margin of error is a popular choice also. For instance, you might see a television poll state that the approval rating of the president is 72%, the margin of error of the poll is plus or minus 3%. If we want the margin of error smaller, i.e., narrower intervals, we can increase the sample size. Or, if you calculate a 90% confidence interval instead of a 95% confidence interval, the margin of error will also be smaller. However, when one reports it, remember to state that the confidence interval is only 90%, because otherwise, people will assume 95% confidence. For 0.90 confidence level, the critical value, 1.645. For 0.95 confidence level, the critical value is 1.96. When you have narrower interval, you have more precision. Recall that when we are looking for population mean, we have two scenarios. Case 1, sigma is known. When the population is normal, or when the sample size is large, and greater than or equal to 30, then, sample mean in approximately normally distributed. Z equals, / square root, where Z has a standard normal distribution. Case 2, sigma is unknown. One way to estimate sigma is by S, the standard deviation of the sample, and replace sigma by S in the above Z equation. However, this new quotient no longer has a Z distribution. Instead, it has a T distribution. We call the following a studentized version of T equals, / square root. Check the conditions. One of the following conditions need to be satisfied. If the sample comes from a normal distribution, then the sample mean will also be normal. In this case, / square root will follow a T distribution with n1 degrees of freedom. If the sample does not come from a normal distribution but the sample size is large, and greater than or equal to 30, we can apply the central limit theorem and state that is approximately normal. Therefore, / square root will follow a T distribution with n1 degrees of freedom. When we do not know the standard deviation of population, we are using T. In T distribution we have north 1 degree of freedom. It represents the number of values in the final calculation of a statistic, df. 3,5,7,100 equals 115/4 equals 28.47. In this example, the degree of freedom, or df, is 3. In this example, once we know the mean of the first 3 data points, the last data point cannot change freely, if we want to keep the overall mean equal to 28.47. Percent confidence interval for the population mean. Plus or minus underscore, / square root, where the T distribution has df equals n1. This interval is also known as the one sample T interval for the population mean. Students' T distribution. We are using T when the standard deviation for population is unknown and sample size is less than 1000. If it is more than 1000, we can use Z distribution and use sample standard deviation as population standard deviation. In probability and statistics, students' T distribution, or simply the T distribution, is any member of a family of continuous probability distributions that arises when estimating the mean of a normally distributed population in situations where the sample size is small and the population standard deviation is unknown. The T distribution is different for different sample size, n. The graph below shows the T distribution for degrees of freedom of 10, blue, and 30, red dashed. The T distribution plays a role in a number of widely used statistical analyses, including students' t-test or t-test for assessing the statistical significance of the difference between two sample means, the construction of confidence intervals for the difference between two population means, and in linear regression analysis. The degrees of freedom refers to the number of independent observations in a set of data which is equal to n. 1. Introduction to inferences. 2. Estimation and confidence intervals. 3. Inference for the population proportion. 4. Inference for the population mean. 5. Students' t-distribution. 6. Chi-square distribution. In probability and statistics, students' t-distribution, or simply the t-distribution, is any member of a family of continuous probability distributions that arises when estimating the mean of a normally distributed population in situations where the sample size is small and the population standard deviation is unknown. The t-distribution is different for different sample size, n. The graph below shows the t-distribution for degrees of freedom of 10, blue, and 30, red dashed. The t-distribution plays a role in a number of widely used statistical analyses, including students' t-test or t-test for assessing the statistical significance of the difference between two sample means, the construction of confidence intervals for the difference between two population means, and in linear regression analysis. The degrees of freedom refers to the number of independent observations in a set of data which is equal to n. 1. Smaller than 1000, if n 1000 t-distribution is very close to z distribution. Properties of the t-distribution. 1.t is symmetric about 0, like z distribution. 2.t distribution is more variable than the standard normal distribution, z distribution. 3.t distributions are different for different degrees of freedom, d.f equals n1. 4. The larger n gets, or as n goes to infinity, the closer the t distribution is to the z distribution. 5. Like 2. The meaning of 2 is the t-value having the area 2 to the right of it. 7. You know that z has a mean of 0 and variance of 1. But for t-distribution the variance is always greater than 1. Although it is close to 1 when there are many degrees of freedom. With infinite degrees of freedom, the t-distribution is the same as the standard normal distribution, z distribution. Example, find where we have 21 observation. The t-distribution is symmetric and bell-shaped, like the normal distribution, but has heavier tails, meaning that it is more prone to producing values that fall far from its mean. FYI 6. The variance is equal to 2 equals 1, 3, where v the degree of freedom and v greater than or equal to 2, v equals n1. So, a t-distribution is not much different from a z-distribution. It is just that a t-curve is shorter and flatter than a z-curve, as shown in this diagram. Method 1. Use this t-table. Equals 1.725. Note: when the corresponding degree of freedom is not given in the table, you can use the value for the closest degree of freedom that is smaller than the given one. We use this approach since it is better to err in a conservative manner, get a t-value that is slightly larger than the precise t-value. Note: when the sample size is larger than 30, the t-values are not that different from the z-values. Thus, a crude estimate for with 34 degrees of freedom is equals 1.645. Although it is a crude estimate, when software is available, it is best to find the t-values rather than use the z. Example: you are interested in the average emergency room, ER, wait time at your local hospital. You take a random sample of 50 patients who visit the ER over the past week. From this sample, the mean wait time was 30 minutes and the standard deviation was 20 minutes. Find a 95% confidence interval for the average ER wait time for the hospital. 1. Check conditions: is the population data normal? We don't know. In order to apply the central limit theorem, we need a large sample. Since n equals 50/30, we can use the central limit theorem. 2. The population standard deviation is unknown, we only know the sample standard deviation. We know that set membership symbol plus or minus tau. But for using this formula we need population standard deviation, since here we don't know, we estimate standard error. by sample standard deviation, estimated SE equals. And in this scenario, we must use t-distribution set membership symbol plus or minus. Having satisfied the conditions, we proceed by finding the proper multiplier from the t-table. With n of 50 the DFR 49, and for 95% confidence, the alpha value is 5% or 0.05. From the t-table under the column 0.025, remember we use alpha/2, and a df of 40, since 49 is not on the table, we arrive at a t-value of 2.021, completing our confidence interval formula. From online calculator, we arrive at a t-value of -2.010 equals 2.01. Shapiro-Wilk test. Tests whether a data sample has a Gaussian distribution. Assumptions. Observations in each sample are independent and identically distributed, id. Interpretation. H0, the sample has a Gaussian distribution. H1, the sample does not have a Gaussian distribution. Chi-square distribution. Sampling distribution of S. 2. Suppose we have a sample with size n taken from normal n, u, sigma. The statistic. Chi-square equals chi. 2 equals 1. 2. 2 equals n1, asterisk. With d.f equals n1. Is called the chi-squared statistic, which have chi-squared distribution. We use chi_square to estimate population standard deviation and for test of independency of two categorical variables. In the following picture, the red curve shows the distribution of chi-square values computed from all possible samples of size 3, v equals 3 to 1 equals 2. The green curve shows the distribution of chi-square values computed from all possible samples of size 5, v equals 5 to 1 equals 4. The blue curve shows the distribution of chi-square values computed from all possible samples of size 11, v equals 11 to 1 equals 10. As the degrees of freedom increase, the chi-square curve approaches a normal distribution. The properties of chi-square distribution. The mean of the distribution is equal to the number of degrees of freedom. E, chi. 2, equals mu equals n1. The variance is equal to 2 times the number of degrees of freedom. Introduction to hypothesis testing. 2 hypothesis test for 1 sample mean. 3 hypothesis test for 1 sample proportion. As mentioned before, methods of making inferences about parameters are either estimating the parameter or testing a hypothesis about the value of the parameter. In this part, we will introduce the concepts of hypothesis testing. Then we will discuss hypothesis testing for a population proportion. And we discuss inference for the population mean. The hypotheses are the most important aspect. If the hypotheses are incorrect, your conclusion will also be incorrect. Suppose we have xn. 2. We don't know the parameters. Take sample x1, x2, x3, xn from above population. One way we can do is we can use the sample building statistics to estimate the parameters. Another way we can use statistical test called hypothesis testing. To answer question like, example, is average body temperature of adults really 37 degrees Celsius? Hypothesis testing allows you to check the statistical credibility of the claims or assumptions. This claim could be a claim by the customer or by a company, or just a form of the popular belief that exists among people. In using hypothesis testing, you can gather evidence in the form of a sample and then prove whether this claim should be rejected or not. We all come across several claims every day. An airline company claims that 90% of its flights are on time. A consultant claims that using just-in-time production can reduce your inventory cost per unit by $10. A tire manufacturer claims that its tires last 50% longer than its competitors. You are probably left wondering how many of these are true. Application of hypotheses testing. Campaign analytics. Analyze if the campaign was effective or not based on the response rate. Let's say an e-commerce company wants to decide between 2 variants of a button. Shop now and buy now. Although it may seem insignificant, practically speaking, it has been observed that improving the UI/UX design can have enormous benefits for the company. In such cases, we perform A/B testing, which is a subset of hypothesis testing. Another important area where hypothesis testing is extensively used is checking the validity of machine learning models. As the course progresses, you will learn how to build and validate various machine learning models. This is where hypothesis testing will come in handy. Any product that you buy comes with a warranty. Electronic products generally come with a 1-year warranty, whereas car manufacturers give a 10-year warranty, depending on the components of the car. These claims are majorly driven by hypothesis testing. Listed below are some important properties of null and alternate hypotheses. The null and alternate hypotheses are always mutually exclusive events. Null hypothesis, H0, the statement is the default assumption/belief, the status quo. Alternate hypothesis, HA, this statement challenges the status quo, i.e., it states the opposite of the null hypothesis. The null and alternate hypotheses must be collectively exhaustive event. The null and alternate hypotheses must be collectively exhaustive events. This means that at least one of these events must be true at any given time. The two events cover the complete sample space. Since these are perfect opposites of each other, we can also call them complementary events. Following are some important points to keep in mind about framing null and alternate hypotheses. The null and alternate hypotheses are perfect opposites of each other. Hence, they should cover the entire range of possibilities. The null hypothesis always has the following signs: equals or less than or equal to or greater than or equal to. The alternate hypothesis always has the following signs: is not equal to or. Note, the null hypothesis always includes an equal sign. So, whenever a new claim is made, the null hypothesis states that the claim is not true, and the alternate hypothesis states that the claim is true. Hence, for the claim to be declared true, evidence will have to be gathered to prove its statistical validity. In other words, the strategy is to frame the alternate hypothesis as the hypothesis that you are trying to prove. We always begin with the assumption that the null hypothesis is true. Then, if we have sufficient evidence to prove that the null hypothesis is false, we reject it. In this case, the alternate hypothesis is proved to be true. If we do not have sufficient evidence to prove that the null hypothesis is false, we fail to reject it. In this case, the assumption that the null hypothesis is true remains. H0, all students are girls. We don't have enough evidence to reject null hypotheses. You understood that we never prove the null hypothesis, we can only say that we fail to reject the null hypothesis based on the evidence that we have gathered. If the evidence supports the claim, we accept the alternate hypothesis, i.e., we reject the null hypothesis. If the evidence does not support the claim, we fail to reject the null hypothesis. Formulating the hypotheses. Suppose you are the CEO of a shoe manufacturing company. An employee has developed a new sole and claims that incorporating it will decrease the wear of the shoe after 3 years of use by more than 9%. Now, you want to test this claim. What will be the null and alternative hypotheses for the sole developed by the employee in this scenario? HO, decrease in wear after 3 years less than or equal to 9%, HA, decrease in wear after 3 years 9%. HO, mu less than or equal to 35 minutes, HA, mu 35 minutes. HO, mu 35 minutes, HA, mu less than or equal to 35 minutes. HO, mu greater than or equal to 35 minutes, HA, mu. It is believed that the average commute time for an employee to and from their office in Toronto is at least 35 minutes. Now, suppose you want to test this claim. What will be the null and alternative hypotheses, considering the average commute time is represented by mu? Goodyear has launched a new tire, which, it claims, can travel more than 7,500 miles before it needs to be replaced. Assuming that the average distance traveled before replacement is given by mu, what would be the null and alternative hypotheses in this case? HO, mu less than or equal to 7,500 miles, HA, mu is not equal to 7,500 miles. HO, mu less than or equal to 7,500 miles, HA, mu 7,500 miles. HO, mu equals 7,500 miles, HA, mu is not equal to 7,500 miles. HO, mu greater than or equal to 7,500 miles, ha, mu. As the claim that the average distance traveled before replacement is more than 7,500 miles is a new claim, we should state it as the alternative hypothesis. Hence, the alternative hypothesis should be stated as more than 7,500 miles, and the null hypothesis should be stated as less than or equal to 7,500 miles. Null hypothesis. The null hypothesis is typically denoted as H0. This hypothesis is assumed to be true until there is evidence to suggest otherwise. Not this is actually initial hypothesis. Alternative hypothesis. The alternative hypothesis is typically denoted as HA or H1. This is the statement that one wants to conclude. It is also called the research hypothesis. The goal of hypothesis testing is to see if there is enough evidence against the null hypothesis. In other words, to see if there is enough evidence to reject the null hypothesis. If there is not enough evidence, then we fail to reject the null hypothesis. So, we have two options. 1. Reject the null hypothesis. 2. Fail to reject the null hypothesis, not having enough evidence to reject null hypothesis. So important. Example. A man, Mr. Orange Juice, goes to trial and is tried for the murder of his ex-wife. He is either guilty or innocent. Set up the null and alternative hypotheses for this example. Answer. Putting this in a hypothesis testing framework, the hypotheses being tested are 1. The man is guilty. 2. The man is innocent. Let's set up the null and alternative hypotheses. H0, Mr. Orange Juice is innocent. Ha, Mr. Orange Juice is guilty. Remember that we assume the null hypothesis is true and try to see if we have evidence against the null. Therefore, it makes sense in this example to assume the man is innocent and test to see if there is evidence that he is guilty. A common format for a hypothesis test is rightward arrow a statement of the null hypothesis, e.g. population mean equals 75 or 2 population means are equal, 1 equals 2 or 1 2 equals 0. Or data is normally distributed. Rightward arrow a statement of the alternative hypothesis, example. Population mean is not equal to 75. 2 population means are not equal, 1 is not equal to 2 or 1 2 is not equal to 0. Data is not normally distributed. Test statistic rightward arrow. The test statistic is based on the specific hypothesis test. We want to know the answer to a research question. We determine our null and alternative hypotheses. Now it is time to make a decision. The decision is either going to be 1. Reject the null hypothesis or 2. Fail to reject the null hypothesis. There is not enough evidence to reject the null hypothesis. Note. Why can't we say we accept the null? The reason is that we are assuming the null hypothesis is true and trying to see if there is evidence against it. Therefore, the conclusion should be in terms of rejecting the null. Assume Health Ministry of Canada country claims that children less than 8 years old don't get one particular disease. Null hypothesis, H0, children less than 8 years old don't get that disease. Alternative hypothesis, ha, less than 8 years old can get that disease. Example, a consumer test agency wants to see whether the mean lifetime of a brand of tires is less than 42,000 miles. The tire manufacturer advertises that the average lifetime is at least 42,000 miles. What is the null hypothesis and alternative hypothesis? Ha, the mean lifetime of a brand of tires is less than 42,000 miles. Consider the following table. The table shows the decision/conclusion of the hypothesis test and the unknown reality, or truth. We do not know if the null is true or if it is false. If the null is false and we reject it, then we made the correct decision. If the null hypothesis is true and we fail to reject it, then we made the correct decision. So what happens when we do not make the correct decision? When doing hypothesis testing, two types of mistakes may be made and we call them type I error and type 2 error. If we reject the null hypothesis when it is true, then we made a type I error, false alarm, false positive. If the null hypothesis is false and we failed to reject it, we made another error called a type 2 error. So important. H0, not being pregnant. As an example, the null hypothesis for anyone is that he/she doesn't have cancer. So if someone got positive for test of cancer, that means we reject null hypothesis. And get this conclusion that he/she has cancer, but there is still chance that test was incorrect. For someone who doesn't have actually cancer, but by mistake got positive. False positive, type I error happened. For someone who has actually cancer, but by mistake got negative, false negative. Type 2 error happened. So important. Types of errors. Type I error. When we reject the null hypothesis when the null hypothesis is true. Type 2 error. When we fail to reject the null hypothesis when the null hypothesis is false. The reality, or truth, about the null hypothesis is unknown, and therefore we do not know if we have made the correct decision or if we committed an error. We can, however, define the likelihood of these events. Alpha. The probability of committing a type I error, rejection of the null hypothesis when the null hypothesis is true. Also known as the significance level. Significance level equals type I error equals alpha equals false positive, as an example predicting cancer for someone who doesn't have cancer, or predicting spam for a non-spam email. Beta. The probability of committing a type 2 error. False negative, as an example predicting not having cancer for someone who has cancer, or predicting non-spam for a spam email. Power is the probability the null hypothesis is rejected given that it is false, i.e. 1 beta. Alpha and beta are probabilities of committing an error, so we want these values to be low. However, we cannot decrease both. As alpha decreases, beta increases. Note: type I error is also thought of as the event that we reject the null hypothesis given the null is true. In other words, type I error is a conditional event and alpha is a conditional probability. The same idea applies to type 2 error and beta. Alpha, beta. Type I error, FP, this error is committed when you reject a null hypothesis that is actually true. The probability of committing a type I error is denoted by the significance level, alpha, of the test. Type 2 error FN, this error is committed when you fail to reject a null hypothesis that is actually false. The probability of committing a type 2 error is denoted by beta. Power equals 1 beta. Effect of confidence level on type I and type 2 errors. Increasing the confidence level of the test decreases the size of the rejection region, thereby lowering the chances of rejecting the null hypothesis, irrespective of whether it is false or not. Hence, increasing the confidence level of the test, say, from 95% to 99%, decreases the probability of committing a type I error. Increasing the confidence level will make it more likely that you fail to reject the null hypothesis. This is because it is difficult to reject the null hypothesis at higher confidence levels. Thus, the probability of committing the type 2 error will increase by increasing confidence level. 1. Type I error decreases. 2. Type 2 error increases by increasing the sample size. 1. Type 2 error decreases. 2. Type I doesn't change. 3. Evidence is increased, and you are more likely to get the correct decision. Let's assume the following hypothesis experiment. H0, the average battery life of life-saving equipment is at most 1 year. The average battery life of life-saving equipment is more than 1 year. A. Which type of error would you like to minimize here, type I error or type 2 error? B. Should you choose a higher confidence interval or a lower confidence interval? A. Type I error. Type I error means we conclude that the battery life is more than 1 year, so it is more dangerous since it is life-saving equipment, but type 2 error means conclude it is at most 1 year, so you may replace its battery sooner than you should and just increase the cost, not risking the life. B. Alpha decreases 1 alpha increases confidence interval increases. A test to screen for a serious but curable disease is similar to hypothesis testing. In this instance, the null hypothesis would be that the person does not have the disease, and the alternate hypothesis would be that the person has the disease. If the null hypothesis is rejected, it means that the disease is detected and treatment will be provided to the particular patient. Otherwise, it will not. Assuming the treatment does not have serious side effects, in this scenario, it is better to increase the probability of Type I error would be providing treatment upon detecting the disease, when the person does not actually have the disease. And type 2 error would be not providing treatment upon failing to detect the disease, when the person, as an example, the null hypothesis for anyone is that he/she doesn't have cancer. So if someone got positive for test of cancer, that means we reject null hypothesis and get this conclusion that he/she has cancer, but there is still chance that test was incorrect. For someone who doesn't have actually cancer, but by mistake got positive, false positive, type I error happened. For someone who has actually cancer, but by mistake got negative, false negative, type 2 error happened. So important. Types of errors. Type I error. When we reject the null hypothesis when the null hypothesis is true. Type 2 error. When we fail to reject the null hypothesis when the null hypothesis is false. The reality, or truth, about the null hypothesis is unknown, and therefore we do not know if we have made the correct decision or if we committed an error. We can, however, define the likelihood of these events. Alpha. The probability of committing a type I error, rejection of the null hypothesis when the null hypothesis is true. Also known as the significance level. Significance level equals type I error equals alpha equals false positive, as an example, predicting cancer for someone who doesn't have cancer, or predicting spam for a non-spam email. Beta. The probability of committing a type 2 error. False negative, as an example, predicting not having cancer for someone who has cancer, or predicting non-spam for a spam email. Power is the probability the null hypothesis is rejected given that it is false, i.e. 1 beta. Alpha and beta are probabilities of committing an error, so we want these values to be low. However, we cannot decrease both. As alpha decreases, beta increases. Note: type I error is also thought of as the event that we reject the null hypothesis given the null is true. In other words, type I error is a conditional event and alpha is a conditional probability. The same idea applies to type 2 error and beta. Alpha, beta. Type I error, FP, this error is committed when you reject a null hypothesis that is actually true. The probability of committing a type I error is denoted by the significance level, alpha, of the test. Type 2 error FN, this error is committed when you fail to reject a null hypothesis that is actually false. The probability of committing a type 2 error is denoted by beta. Power equals 1 beta. Effect of confidence level on type I and type 2 errors. Increasing the confidence level of the test decreases the size of the rejection region, thereby lowering the chances of rejecting the null hypothesis, irrespective of whether it is false or not. Hence, increasing the confidence level of the test, say, from 95% to 99%, decreases the probability of committing a type I error. Increasing the confidence level will make it more likely that you fail to reject the null hypothesis. This is because it is difficult to reject the null hypothesis at higher confidence levels. Thus, the probability of committing the type 2 error will increase by increasing confidence level. 1. Type I error decreases. 2. Type 2 error increases by increasing the sample size. 1. Type 2 error decreases. 2. Type I doesn't change. 3. Evidence is increased, and you are more likely to get the correct decision. Let's assume the following hypothesis experiment. H0, the average battery life of life-saving equipment is at most 1 year. The average battery life of life-saving equipment is more than 1 year. A. Which type of error would you like to minimize here, type I error or type 2 error? B. Should you choose a higher confidence interval or a lower confidence interval? A. Type I error. Type I error means we conclude that the battery life is more than 1 year, so it is more dangerous since it is life-saving equipment, but type 2 error means conclude it is at most 1 year, so you may replace its battery sooner than you should and just increase the cost, not risking the life. B. Alpha decreases 1 alpha increases confidence interval increases. A test to screen for a serious but curable disease is similar to hypothesis testing. In this instance, the null hypothesis would be that the person does not have the disease, and the alternate hypothesis would be that the person has the disease. If the null hypothesis is rejected, it means that the disease is detected and treatment will be provided to the particular patient. Otherwise, it will not. Assuming the treatment does not have serious side effects, in this scenario, it is better to increase the probability of type I error would be providing treatment upon detecting the disease, when the person does not actually have the disease. And type 2 error would be not providing treatment upon failing to detect the disease, when the person actually has the disease. Since the treatment has no serious side effects, type I error poses a lower health risk than type 2 error, as not providing treatment to a person who actually has the disease would increase his/her health risk. As you can see here, the type I error, putting an innocent man in jail, is the more serious error. Ethically, it is more serious to put an innocent man in jail than to let a guilty man go free. So to minimize the probability of a type I error, we would choose a smaller significance level. Threshold equals 12. Assume you conduct binary classification for prediction of specific disease. That means at the end of project, you want to predict for new person that he/she has that disease or not, so having disease is positive class. And not having that disease is negative class. Based on all features you calculate y, then based on the value of y you predict. Assume you consider y equals 12 as a threshold. That means for people that have y less than 12, you predict negative, and for people with value of y bigger than 12 you predict positive. By changing threshold, you can decrease one of them and increase the other one. As an example, in spam detection project, since FP is more dangerous, we may increase threshold. If we change threshold from 0.5 to 0.70, FP will be decrease but FN will be increase. In breast cancer prediction, since FN is more dangerous, we may decrease threshold. If we decrease threshold, FN will be decrease but FP will be increase. In data mining course, you will learn confusion matrix and definition of accuracy, recall, precision, and F measure. For test of normality, always null hypotheses, data is normally distributed. So, if p-value significant level. For any test of independency, chi-square, t-test, ANOVA, null hypotheses, those two variables are independent. So, if p-value hypothesis test for one sample mean, hypothesis test for one sample proportion. Let's back to stat. Example, a political news company believes the national approval rating for the current president has fallen below 40%. What is null hypothesis and what is alternate hypothesis? Answer. The response variable here is approval rating and is a qualitative variable. Therefore, we will set up the hypothesis in terms of p. In this case, the p0 value is 0.4 and the hypothesis would be set up as a left-tailed test. P. Let's back to stat. Example, a political news company believes the national approval rating for the current president has fallen above 60%. What is null hypothesis and what is alternate hypothesis? Answer. P 0.60 H0 P equals 0.6, or H0 P less than or equal to 0.6. Right-tailed test. 6. Let S back to stat. Example, a political news company believes the national approval rating for the current president is not 60% anymore. What is null hypothesis and what is alternate hypothesis? Answer. P is not equal to 0.60 H0 P equals 0.60. Two-tailed test. Recall that for unknown population standard deviation, if we have some conditions, we use t-distribution. Hint, in two-tailed test for unknown population standard deviation we would reject the H0 in favor of HA. If the t-value is less than dash 2 or greater than 2, we can find 2. We call it, by using t-table or online calculator for t. And based on sample mean we can find t-value, we call it, by using following formula. Equals. For whole of sample we calculate, based on sample mean and sample standard deviation and sample size. Note, before using this formula make sure 1. The population is normal, or 2. You have enough observation, i.e. sample size equals n greater than or equal to 30, to rely on CLT, central limit theorem. Note, if you have population standard deviation you can use Z formula. Comparing two population means. Comparing two population proportions. Chi-square test of independence. Correlation. ANOVA. So far in our course, we have only discussed measurements taken in one variable for each sampling unit and comparing them with population or estimating for population. This is referred to as univariate analysis. In this lesson, we are going to talk about measurements taken in two variables for each sampling unit. This is referred to as bivariate analysis or bivariate data. Examples: sex and whether they smoke, GPA and the current degree level of a student, dieting and the participant's weight before and after. Find out the relationship, association or correlation, between two variables. Look for association between variables at predefined significance level. Perform bivariates analysis for any combination of categorical and continuous variables. Continuous and continuous. Categorical and categorical. Categorical and continuous. Different methods are used to describe these combinations. Continuous vs continuous. What is correlation? Strength of association between two numerical variables. Pearson correlation shows you the strength of linear relationship. A zero correlation does not imply that there is no relation between variables, it merely indicates that there will no linear relationship between them. Also, there can be a negative or positive correlation between variables. A negative correlation means that if the value of one variable increases, the value of another decreases, whereas it is the opposite for a positive correlation. Now, the higher the coefficient of correlation between numerical variables, the higher the linear relation between them. The pairs of scores can be listed in a table or presented in a scatter plot. Scatter plots can also tell us about the form, shape, of the relationship. The correlation measure tells us about the direction of the relationship between the two variables. The direction can be positive or negative. Positive: in a positive relationship both variables tend to move in the same direction. If one variable increases, the other tends to also increase. If one decreases, the other tends to also. Negative: in a negative relationship the variables tend to move in the opposite directions. If one variable increases, the other tends to decrease, and vice versa. The direction of the relationship between two variables is identified by the sign of the correlation coefficient for the variables. Positive relationships have a plus sign, whereas negative relationships have a minus sign. Sign of correlation is the same as sign of slope of best fit line, but magnitude of correlation in not related to value of slope, _2_1, /_2_1, infinity to plus infinity, but correlation is between 1 to plus 1. The correlation coefficient R is in between -1 and +1. +1 is the largest positive correlation when all points fall in exact one line with positive slope, and -1 is the largest negative correlation that is possible when all points are located exactly on one line with negative slope. 0.5 less than or equal to R, high linear correlation. 0.3 less than or equal to R. R equals +1 or -1, perfect linear relationship. Strong positive correlation. Description: points on the scatter plot form a tight, upward sloping cluster. Weak positive correlation. Description: points on the scatter plot show a general upward trend but are more scattered. No correlation, zero correlation. Description: points on the scatter plot are scattered with no clear trend. Remember that correlation strength is not only about the tightness of the pattern but also about its consistency. Two specific strengths are: perfect relationship: when two variables are exactly, linearly, related, the correlation coefficient is either +1 or -1. They are said to be perfectly linearly related, either positively or negatively. No relationship: when two variables have no linear relationship at all, their correlation is zero. From the correlation matrix below, you can observe that petal length has a high correlation with sepal length, with a correlation coefficient of 0.87. Also, there is a very high correlation coefficient of 0.96 between petal width and petal length. Note, the value of the correlation between petal length and sepal width is -0.43 and not 0.43 at both the places of the below correlation matrix. However, the correlation matrix has its own limitations where you cannot see the exact distribution of a variable with another numeric variable. To solve this problem, we use pair plots. Pair plots are scatter plots of all numeric variables in a data set. It shows the exact variation of one variable with respect to the others. You can observe how one variable is varying with respect to another in the image below. Correlation is not causation. Correlation is a statistical technique which tells us how strongly the pair of variables are linearly related and change together. It does not tell us why and how behind the relationship, but it just says the relationship exists. Causation takes a step further than correlation. It says any change in the value of one variable will cause a change in the value of another variable, which means one variable makes other to happen. It is also referred as cause and effect. Just after finding correlation, don't draw the conclusion too quickly. Take time to find other underlying factors, as correlation is just the first step. Find the hidden factors, verify if they are correct, and then conclude. HTTP URL. Ice cream sales is correlated with homicides in New York, study. In some cases there are some hidden factors which are related on some level. Like in our example of ice cream sales and homicide rates, weather is the hidden factor which is causing both the things. Weather is actually causing the rise in ice cream sales and homicides. As in summer, people usually go out, enjoy nice sunny day and chill themselves with ice creams. So when it's sunny, wide range of people are outside and there is a wider selection of victims for predators. How do we confirm causation between the variables? By using experimental study or observational study. To calculate the Pearson product moment correlation, one must first determine the covariance of the two variables in question. Next, one must calculate each variable's standard deviation. The Pearson correlation coefficient is determined by dividing the covariance by the product of the two variables' standard deviations. A correlation coefficient measures the degree, strength, of the relationship between two numerical variables. The Pearson correlation coefficient measures the strength of the linear relationship between samples of two variables. The formula for Pearson correlation coefficient of variable xy is: there are several correlation coefficients. Pearson correlation coefficient is sensitive only to a linear relationship between two variables, which may exist even if one is a nonlinear function of the other. Rank correlation coefficients, example Spearman's rank correlation coefficient and Kendall-Chow rank correlation coefficient. These are the alternatives to Pearson's coefficient, used either to reduce the amount of calculation or to make the coefficient less sensitive to non-normality in distribution. The Pearson correlation technique works best with linear relationships. As one variable gets larger, the other gets larger, or smaller, in direct proportion. It does not work well with curvilinear relationships, in which the relationship does not follow a straight line. An example of a curvilinear relationship is age and healthcare. They are related, but the relationship doesn't follow a straight line. H.R. Sometimes the relationship is not linear, but x and y follow same direction or opposite direction. For example, in following data, if x increases, y also increases, although it is not linear relationship. In this situation, rank correlation is better metric. Rank correlation coefficients, such as Spearman's rank correlation, measure the extent to which as one variable increases, the other variable tends to increase, without requiring that increase to be represented by a linear relationship. If as the one variable increases, the other decreases, the rank correlation coefficients will be negative. The Spearman's rank correlation coefficient is appropriate for both continuous and discrete variables, including ordinal variables. The rank correlation coefficient between two variables will be high when observations have a similar rank, or identical for a correlation of 1, between the two variables, and low when observations have a dissimilar rank, or fully opposed for a correlation of -1, between the two variables. That means if we want to predict petal length only based on sepal length, you can use following formula. This is SLR, simple linear regression. That means we can only explain 76% of the variation in petal length by sepal length. That means there are some more features that can explain 24% of the variation in petal length, but we don't have them in our model. Since I used more than one predictor, this is called MLR, multiple linear regression. R-square is between 0 and 1, the closer to 1 the better model, but for MLR you should better compare adjusted R-square. Chi-square test for independence. How do we test the independence of two categorical variables? It will be done using the chi-square test of independence. As with all prior statistical tests, we need to define null and alternative hypotheses. Also, as we have learned, the null hypothesis is what is assumed to be true until we have evidence to go against it. In this lesson, we are interested in researching if two categorical variables are related or associated, i.e., dependent. Therefore, until we have evidence to suggest that they are, we must assume that they are not. This is the motivation behind the hypothesis for the chi-square test of independence. H0, in the population, the two categorical variables are independent. In the population, the two categorical variables are dependent. Note: there are several ways to phrase these hypotheses. Instead of using the words independent and dependent, one could say there is no relationship between the two categorical variables versus there is a relationship between the two categorical variables. Or there is no association between the two categorical variables versus there is an association between the two variables. The important part is that the null hypothesis refers to the two categorical variables not being related, while the alternative is trying to show that they are related. Note: keep in mind that this chi-square test, when significant, only provides statistical evidence of an association or relationship between the two categorical variables. Do not confuse this result with correlation, which refers to a linear relationship between two quantitative variables. The primary method for displaying the summarization of categorical variables is called a contingency table. When we have two measurements on our subjects that are both the categorical, the contingency table is sometimes referred to as a two-way table. How do we test the independence of two categorical variables? It will be done using the chi-square test of independence. Once we have gathered our data, we summarize the data in the two-way contingency table. This table represents the observed counts and is called the observed counts table, or simply the observed table. Then calculate expected count for each cell under the null hypothesis. Recall that if event A and event B are independent, P, A and B, equals P, A, asterisk P, B. So we can calculate expected value by assuming they are independent. Under the null hypothesis and certain conditions, discussed below, the test statistic follows a chi-square distribution with degrees of freedom equal to R1, C1, where R is the number of levels for variable that mentioned on rows and C is the number of levels for variable that mentioned on columns. We leave out the mathematical details to show why this test statistic is used and why it follows a chi-square distribution. Note: we do not expect you to calculate the critical value or the p-value by hand. The p-value can be found using software. Conditions for the validity of chi-square test. The chi-square test statistic can be used if the following conditions are satisfied. If you do not met the condition, you can use Fisher exact test. 1n, the total frequency, should be reasonably large, say greater than 50. 2. The sample observations should be independent. This implies that no individual item should be included twice or more in the sample. 3. No expected frequencies should be small. Small is a relative term. Preferably each expected frequencies should be larger than 10, but in any case not less than 5. Some statisticians hesitate to use the chi-square test if more than 20% of the cells have expected frequencies below 5, especially if the p-value is small and these cells give a large contribution to the total chi-square value. Are the results of my chi-square test of association invalid? If either variable has only 2 or 3 levels, then you can trust the results if either of the following is true: all cells have expected counts of at least 3. All cells have expected counts of at least 2, and 50% or fewer of the cells have expected counts of less than 5. If both variables have 4 to 6 levels, then you can trust the results if either of the following is true: all cells have expected counts of at least 2. All cells have expected counts of at least 1, and 50% or fewer of the cells have expected counts of less than 5. Categorical and categorical. For example, we want to find out, is there any association between cancelling method, by phone or online, and churn? Yes or no. Yes means that customer cancelled his/her contract. Null hypothesis: there is no association between those two categorical variables. To find the relationship between two categorical variables, use following methods. Two-way table: create two-way table of count and percent count. The rows represent the category of one variables and the column represent the category of the other variable. Show count or percent count of observations available in each combination of row and column categories. Chi-square test, to derive statistical significance of relationship between two categorical variables. Also tests how strong the evidence in the sample to generalize that relationship for a larger population. Chi-square is based on the difference between the expected and observed frequencies in one or more categories in the two-way table. Probability of 0, both categorical variable are dependent. Probability of 1, both variables are independent. Null hypothesis, there is no association between those two categorical variables. If all assumptions are met and p-value. Use KISK as an option with PROC frequency to perform this test. Hint, before interpreting a result of any test, you must be sure that all assumptions for that test are met. Assumption of chi-square test. Tables larger than 2x2. Each observation is independent of all the others, i.e., one observation per subject. I mean you can't have observation that counted in more than one levels as an example in hard data set. If we assume moderate, 6 to 20, and heavy, 16 and more, you can't rely on the result of chi-square, because if someone smokes 18 cigarettes he/she belongs to two groups. No more than 20% of the expected counts are less than 5 and all individual expected counts are 1 or greater. Yates, Moore and McCabe, 1999, p. 734. 2x2 tables, the standard advice. The standard advice for 2x2 tables dates back to Cochrane, 1952, 1954, or earlier, and goes something like this. Each observation is independent of all the others, i.e., one observation per subject, asterisk. All expected counts should be 10 or greater. If any expected counts are less than 10, but greater than or equal to 5, some authors suggest that Yates correction for continuity should be applied. This is done by subtracting 0.5 from the absolute value of OE before squaring. However, the use of Yates correction is controversial, and is not recommended by all authors. If any expected counts are less than 5, then some other test should be used. Example: Fisher exact test for 2x2 contingency tables. Imagine you have one categorical variable, like sex, male and female, and one continuous variable, weight. Bivariate analysis for the scenario test. Here you are going to check H0, the mean of white is equal between male and female. The mean of weight is not equal between male and female. Checking assumption or condition, normality 2. Equality or homogeneity of variance, it means check the equality of white variance between male and female. Continuous variable, cholesterol, ANOVA, analysis of variance. Categorical variable, smoking, 5 level. H0, the mean of cholesterol is the same in different categories of smoking. The mean of cholesterol is not equal or it is not same in different categories of smoking. Imagine you have one categorical variable, like sex, male and female, and one continuous variable, weight. Bivariate analysis for the scenario test. Here you are going to check H0, the mean of white is equal between male and female. The mean of weight is not equal between male and female. Checking assumption or condition, normality 2. Equality or homogeneity of variance, it means check the equality of white variance between male and female. Continuous variable, cholesterol, ANOVA, analysis of variance. Categorical variable, smoking, 5 level. H0, the mean of cholesterol is the same in different categories of smoking. The mean of cholesterol is not equal or it is not same in different categories of smoking. Exploratory data analysis, EDA. Group box plots. Draw box plots for each level of categorical variables. Visualize the distribution of the continuous variable across different categories. Check assumptions. Ensure the assumptions of the statistical tests are met. Example: normality, homogeneity, or equality of variances, equal variance labeled, pooled, the other under the assumption of unequal variance, labeled Satterthwaite. Statistical analysis. Statistical significance. To assess statistical significance, perform z-test/t-test or ANOVA. Determine the appropriate test based on the number of levels in the categorical variable. For categorical variable with 2 levels, binary. Run a t-test to assess whether the means of the two groups are statistically different. For categorical variable with more than 2 levels, run ANOVA, analysis of variance, to assess overall differences in means among the multiple groups. Z-test/t-test. One purpose. Assess whether the mean of 2 groups are statistically different from each other. 2 selection criteria. Choose between z-test and t-test based on sample size and whether the population standard deviation is known. Z-test for larger sample sizes with known population standard deviation. T-test for smaller sample sizes or when the population standard deviation is unknown. In the output of t-test you can see 4 table. The first one is descriptive statistics of continuous variable between different category of categorical variable. In that table you can see the difference of mean between 2 levels. Move on to the 4th table, it is equality of variance. Check the p-value. If it is less than 0.05 it means you should reject. Null hypothesis, in other words the variance of BMI is not equal between stroke 0 and stroke 1. So you will move to table number 3 and report the p-value for Satterthwaite test. It is less than 0.05, so it means the mean of BMI is not equal between 2 levels of stroke, so the difference of -1.77 is statistically significant. Assumption: the independent 2-sample t-test assumes variance of the data in both groups should be approximately equal. It means that the spread of data points around the mean should be similar for both groups. Equality of variances table: since the p-value of the equality of variances test, 0.9527, is greater than the significance level, example 0.05, then we assume that the variances are equal. In this case we will use pooled method. If the p-value had been less than 0.05, we would have used the Satterthwaite method. ANOVA analysis of variance, or ANOVA, is a statistical method that analyzes variances to determine if the means from more than 2 populations are the same. In other words, we have a quantitative response variable, y, and a categorical explanatory variable, x, with more than 2 levels. Continuous dependent and categorical is independent. Use SASPROC ANOVA. Let's assume you are a data scientist who work in data science department of Walmart. Scenario number 1, you want to find is there any associate between amount of order and method of buying. If you offer 2 methods, online and in store, so you should run t-test because you want to find relationship between categorical variable, method, and continuous variable, order, amount, and that categorical variables have only 2 levels. Scenario number 2, you want to find is there any associate between amount of order and province, so you should run ANOVA because you want to find relationship between categorical variable, province, and continuous variable, order, amount, and that categorical variables have more than 2 levels. Comparing 2 population parameters taken from 2 distinct groups. 1. Categorical, taken from 2 distinct groups. If the measurements are categorical and taken from 2 distinct groups, the analysis will involve comparing 2 independent proportions. 2. Quantitative, taken from 2 distinct groups. If the measurements are quantitative and taken from 2 distinct groups, the analysis will involve comparing 2 independent means taken twice from same subject, paired. 3. Quantitative, taken twice from each subject, paired. If the measurements are quantitative and taken twice from each subject, the analysis will involve comparing 2 dependent means. 4. Categorical, taken twice from each subject, paired. If the measurements are categorical and taken twice from each subject, the analysis will involve comparing 2 dependent proportions. Outcome, or y, or dependent or response variable equals weight, continuous variable. Explanatory, or x, or independent variable equals diet, categorical variable with 2 level. To begin, one has to first decide whether the problem you are investigating requires the analysis of categorical or quantitative data. In other words, you need to identify your response variable and determine the type of variable. Next, one has to determine if the 2 measurements are from independent samples or dependent samples. Examples: 1. Sex and whether they smoke. Consider a case where we measure sex and whether they smoke. In this case, the response variable, smoking status, is categorical and taken from 2 distinct groups, and the explanatory variable, sex, is also categorical. Response variable, target yes or no to the question do you smoke. Explanatory variable, sex, female or male. 2. GPA and the current degree level of a student, graduate or undergraduate. In this case, the response variable, GPA, is quantitative and taken from 2 distinct groups, and the explanatory variable, degree level, is categorical. Response variable, GPA. Explanatory variable, graduate or undergraduate. 3. Dieting and the participant's weight before and after. In this case, the response, weight, is quantitative and taken twice from each subject, paired. Response variable, weight. Explanatory variable, diet. In this situation we run paired t-test because categorical variables has only 2 levels. The decision process will be the same as well. Method number 1, if the test statistic falls in the rejection region, we will reject the null hypothesis. Method number 2, if the p-value is less than the level of significance, we will reject the null hypothesis. Method number 3, the interpretation of confidence intervals in support of the hypothesis decision will also be familiar. If the interval does not contain the null hypothesis value, then we will reject the null hypothesis. If the interval contains the null hypothesis value, then we will fail to reject the null hypothesis. When comparing two proportions or two means, by default we will use a null value of 0, i.e., no difference, i.e. there is no association between those two variables. For example, 1, 2 equals 0 would mean that 1 equals 2, and there would be no difference between the two population parameters. Similarly, for two population proportions. Although we focus on the difference equaling 0, it is possible to test for specific values of the difference using the methods presented. However, most applications research only for a difference in the parameters, i.e., the difference is less than, greater than, or not equal to 0. Comparing two population mean. Categorical vs continuous. For comparing equality or difference between the mean of two independent sample we use t-test, for only 2 levels, ANOVA, for more than 2 levels. Now suppose we have 2 independent samples and the standard deviation or sigma for population is unknown and sample size is small and we cannot rely on CLT, we want to know can we use the pooled variance method for estimating of standard deviation for population or we should use unpooled, or unequal, variances method. In that case we should run Laven's or Bartlett's test, as Laven's is less sensitive to departures from normality we can use it in most cases. Parametric assumptions. Parametric tests have the same assumptions, or conditions, that need to be met in order for the analysis to be considered reliable. Parametric test assumptions. 1. Independence. 2. Population distributions are normal, normality. 3. Samples have equal variances, homogeneity of variances. It is best to check the assumptions in the order above since some equal variance tests are sensitive to the distribution being normal. Independence. This assumption is checked during the setup of the study. It means that each observation is independent of another, if there are 2 or more groups being compared. Then it refers to that fact that groups are mutually exclusive, i.e. each individual belongs to only one group, and that the data is not repeated over time. If data is repeated measures, longitudinal/panel or time series, there are appropriate methods, like paired t-test, to account for the repeated data points from individuals. This is typically handled in the math of the statistical test that is designed to analyze this type of data. Normality. The normality assumption is applied differently depending on the statistical method being used. For example, it applies to the shape of the sampling distribution for the dependent variable, outcome variable, if it's a univariate test, to the difference scores if it's mean comparison, EX independent sample t-test or paired t-test, or to the residuals if it's a regression framework. This assumption can be checked with a formal test or graphically. There are a few formal tests that can be used to check this assumption. Before that gets touched, the central limit theorem needs to be discussed. Ott and Longnecker, 2010, p.188. Provide this overview about the central limit theorem. Note. 1. For paired t-test you should check normality for differences of each EU, experimental units, /subject. 2. For independent t-test and ANOVA you should check normality for each groups, but if you have many groups, a 2x2x3 ANOVA has 12 groups, or if there are few observations per group, it's hard to check normality. On only 20 data points, it's often easier to just use the residuals and check them all together. 3. In regression you should check normality for residual. No specific shape was required for these measurements for the central limit theorem to be validated. Great, what does it mean though? It means that if the sample size is large enough then normality may not be a concern even if the test for normality indicates that normality is not present. Simulation studies have been conducted and the general rule of thumb is n greater than or equal to 30. However, if it's clear that there is heavy skewness or kurtosis, one might consider transforming the data and/or using a non-parametric statistical test. There are a number of techniques that you can check if your data sample is Gaussian or sufficiently Gaussian like to use the standard techniques, or sufficiently non-Gaussian to instead use non-parametric statistical methods. This is a key decision point when it comes to choosing statistical methods for your data sample. We can summarize this decision as follows. Normality tests. There are many out there to choose from. These include 1. Shapiro-Wilk test, 2. Kolmogorov-Smirnov, KS test, Lilliefors corrected KS test, Anderson-Darling test, D'Agostino-Scunis test, D'Agostino-Pearson omnibus test, and the Yark-Barrett test. This section will not cover all of these, but will demonstrate common normality tests. Additionally, normality tests should be accompanied by a visual test as well. For visualization you can use histogram. A sample of data has a Gaussian distribution of the histogram plot, showing the familiar bell shape, or you can use QQ plot. Quantile plot. Another popular plot for checking the distribution of a data sample is the quantile plot, QQ plot, or QQ plot for short. This plot generates its own sample of the idealized distribution that we are comparing with, in this case, the Gaussian distribution. The idealized samples are divided into groups, called quantiles. Each data point in the sample is paired with a similar member from the idealized distribution at the same cumulative distribution. The resulting points are plotted as a scatter plot with the idealized value on the x-axis and the data sample on the y-axis. Shapiro-Wilk test. The Shapiro-Wilk test evaluates a data sample and quantifies how likely it is that the data was drawn from a Gaussian distribution, named for Samuel Shapiro and Martin Wilk. In practice, the Shapiro-Wilk test is believed to be a reliable test of normality, although there is some suggestion that the test may be suitable for smaller samples of data, e.g. thousands of observations or fewer. Tests whether a data sample has a Gaussian distribution. Assumptions. Observations in each sample are independent and identically distributed, id. Interpretation. H0, the sample has a Gaussian distribution. H1, the sample does not have a Gaussian distribution. The Shapiro-Wilk test. So if p-value is less than 5% you can reject normality, and if p-value is bigger than 5% normality assumption is met. D'Agostino's K-2 test. The D'Agostino's K-2 test calculates summary statistics from the data, namely kurtosis and skewness, to determine if the data distribution departs from the normal distribution, named for Ralph D'Agostino. Skew is a quantification of how much a distribution is pushed left or right, a measure of asymmetry in the distribution. Kurtosis quantifies how much of the distribution is in the tail. It is a simple and commonly used statistical test for normality. Assumptions. Observations in each sample are independent and identically distributed, id. Interpretation. H0, the sample has a Gaussian distribution. H1, the sample does not have a Gaussian distribution. Anderson-Darling test. Anderson-Darling test is a statistical test that can be used to evaluate whether a data sample comes from one of among many known data samples, named for Theodore Anderson and Donald Darling. It can be used to check whether a data sample is normal. The test is a modified version of a more sophisticated non-parametric goodness of fit statistical test called the Kolmogorov-Smirnov test. A feature of the Anderson-Darling test is that it returns a list of critical values rather than a single p-value. This can provide the basis for a more thorough interpretation of the result. Assumptions. Observations in each sample are independent and identically distributed, id. Interpretation. H0, the sample has a Gaussian distribution. H1, the sample does not have a Gaussian distribution. As with testing the assumption of normality, there are a few statistical tests available to test the assumption of equal variances. Some common methods are the Bartlett test and Levine's test for equality of variances. Choosing the correct test is also dependent on the assumption of normality. For example, Bartlett's test has been found to be sensitive to departures from normality whereas Levine's test is less sensitive to this, Conover, 1981. It doesn't matter if one is coming from a two-sample approach or a regression/ANOVA approach, the test steps are the same. One needs to test for equality of variance for each categorical variable on the outcome. Homogeneity of variances. What if homogeneity of variances is violated? If there is not equal variances between groups, there are a few routes to consider. These are in no particular order.